Welcome back. In this video we'll just review everything that we've learned in Unit 2, and while ideally I would like to keep this video short, in reality Unit 2 is a massive unit, possibly the biggest unit in AS actually. So realistically it's not going to be possible, to keep this video under an hour, for example. Therefore I would recommend, if you do watch the whole thing, then probably watch it at least 1.5 or even 2 times the speed. Right, so just a quick overview of what we're going to cover. So we need to understand the benefits of different networking devices, right? We need to compare LAN and WAN, right? Local area network, wide area network. We're going to look at client server, peer-to-peer, right? Also thin client, thick client, difference between them. Right, the different topologies, so bus, star, mesh, hybrid, I guess also point-to-point. Right, we're going to look at cloud computing. We're going to compare wired and wireless. Right, we're going to look at the hardware used on a LAN. We're going to look at the function of a router. Right, also we'll look at Ethernet, how collisions are handled, so CSMA CD, right, carrier sense multiple access with collision detection. Right, we'll look at bit streaming, so real-time and on-demand bit streaming. We're going to look at the differences between World Wide Web and Internet. Again, the hardware, okay, so the hardware for a LAN, also the hardware for, kind of the global Internet. Right, we're going to look at, different IP addresses, IP version 4, IP version 6. Then we'll look, URLs, World Wide Web, right, DNS, I think also DHCP. Also NAT, right, network address translation. Alright, so actually I will say, if you haven't watched the other videos, then probably this video is going to be, let's say, too fast. So it's not going to cover the content, right, in enough detail. So this video does assume that either you've read the book, or you've watched the previous videos. If you come into this, thinking, I can learn all of networking in, say, 2-3 hours, however long this is going to be. That's probably not going to be realistic, since again, this whole continent is probably 15 hours of class time. Right, anyway, quickly then, so if we think, what is a network? The definition is simple, right, just 2 or more devices connected together, and if you say that in the exam, that should be 2 marks. Right, the connection, could be either wired or wireless, and of course, we'll look at different types of those. Right, then let's think, what are clients and servers? So a client, is going to be a device that's requesting or asking for something. Right, a server, a device responding to or fulfilling that request. Right, e.g., a client could be sending a request for a website, and the website would then respond with the web page to them. And I suppose here, when we say the website, in this case the website, that's going to be the web server. So the client would be the browser, right, us. The server, that's the web server that's responding with that web page. Right, so if we look at some of the different networking features, one is just communicate. So I guess 2 devices, sending files, sending messages to each other, and that can be both within the network, so within the network, right, sending to other devices right on the same LAN, or kind of on a WAN, right, the sort of global internet, sending messages from our device to a device on another network, right, to a server, right, web server. Right, I guess we can also have a file server on the network, so to share files with those on the network. Right, an application server, so software could be installed in one location, but it can be used by everyone in the network, for example, in the company, in the school, in the hospital. Right, an email server, basically just to store emails, right, store the different email accounts. Okay, so that's going to allow sending, receiving, and storing emails internally. And the benefit of that, now, let's say if you're a company, or like a government or some, so even a school. Now, maybe you don't want to use, for example, Gmail because you're worried about privacy. Also, having your own email server, if you set up, so you have, the domain as well, then you're going to have, your name, at, for example, yourcompany.com, rather than being at gmail.com. And of course, that's going to be more professional, right, having your own sort of website domain, as part of the email address. We're also a database server, to host database internally, again, for privacy reasons. Not wanting to host, on another person's computer or server. And then, print server. So when it says print server, I mean basically just a printer. That's going to allow many computers or many devices to use one printer, rather than having an actual physical, for example, I don't know, like Ethernet connection, right, between the computer and the printer. They can just connect wirelessly. They can all send their documents to the printer to be printed. Right, then if we look at the different types of network, so smallest to biggest, right, PAN, hopefully people remember this, personal area network, basically just Bluetooth, that's going to be the obvious one. Right, LAN, local area network, e.g. a router or a switch, I guess in one building or one room, for example in a classroom. Then a MAN, that's a metropolitan area network, so this is basically, a network in one city, and usually it's going to be in different locations throughout that city. So let's say you have a university. Now maybe this university has multiple campuses scattered throughout the same city. That's going to be a MAN. Now this could also be, let's say if you have free Wi-Fi on the subway. Well, in that case, if you get city-wide coverage, right, yeah, that's also going to be a MAN. Rather than finally, well, just a WAN, right, wide area network, so well, multiple cities, multiple countries, and hopefully people remember, well, the internet is also just considered a WAN, yeah, kind of a global WAN. Right, so I guess, well, the exam generally only asks about LANs and WANs, although I think maybe once or twice I have seen them ask, well, yeah, what's a PAN, right, what's a MAN? So yeah, just make sure you're familiar with those as well. Alright, so I think, well, quickly let's talk about, well, LANs and WANs, because again, well, the other two are, yeah, not that common. Right, so this is a network within the same building. Right, nodes, so, yeah, okay, so when it says nodes, well, basically devices or anything connected to it. Right, nodes don't necessarily have to be connected, well, to sort of the global internet. They could just be connected internally, right, to each other. And if they're just connected to other devices on the network, well, then it's an intranet. If this LAN is also connected, let's say, to the global internet, well, yeah, then it's going to be internet. And if we think, well, inter means, right, between, so I guess, yeah, sort of multiple different networks connected together. Intra, well, this means internal, so I guess, yeah, just one network. Right, I guess, well, Wi-Fi and Ethernet, so, well, twisted pair are going to be the most common connection methods. And again, some of the different types of server, well, application server, file server, print, email server, yeah, can be used, well, to share those different things. Yeah, okay, all right, so I think, yeah, that we mentioned. Right, just an example, so here we've got a router in the middle, and I suppose actually if you just wanted a LAN, I mean, you could say this is just a switch in the middle. Now, a switch can be used just kind of internally, yeah, just for one device on the network to send to another device on the network. Now, if we want to send from our network to another network, well, that's when we're going to need a router. Because if we think, well, routers, they're going to take what the destination IP address and then just, you know, send it to the next hop, right? Send it to the next device. And obviously, well, in this example, we can see what we got, yeah, various different devices connected. And in this case, well, since it's a router, yeah, we can also see, well, therefore, that's also connected, right, to the global internet. Right, then if we look at WAN, so well, wide area network, computers can be on the other side of the world, yeah, kind of global coverage. Right, it's going to allow, well, again, sort of sharing of file software, right, between all of those on the network. Right, you can also have a job, or I guess a process, that can be run on a remote computer that had the required software, right, e.g. processing some data. So let's imagine you've got, I don't know, some specialist like supercomputer or, yeah, some like weather processing computer. Well, if, let's say, you want to, I don't know, yeah, process the sort of weather data, or if you want to, you know, render some video, well, then I guess you can send a command, right, to that remote computer, yeah, just so it can, you know, do that processing or, yeah, render that video. And traditionally, well, WANs are going to be slower than LANs, although these days this is less of an issue. For example, with, well, 100 gigabit per second connections, yeah, fibre optic cables, etc., just connecting the different WANs together. Right, and I guess more so, actually, traditional locations would also be connected, well, via leased lines, and they'd be rented from, well, the PSTN, public switch telephone network, right, cable company or government. Now, when we say leased lines, what basically that means you're kind of renting one of these individual telephone lines. Yeah, and I guess really, right, yeah, okay, so when it says traditionally, that's really only going to be for, well, sort of, yeah, big companies, governments. If you're a small company, well, you're not going to be able to afford, right, a dedicated line spanning, you know, what, sort of hundreds or thousands of kilometers. But yeah, I guess, well, yeah, okay, so again, for big companies, governments, yeah, that's really going to be an option. Although these days, well, fibre optic cables are often used, right, therefore I think the sort of shared infrastructure isn't so much of an issue, right, in terms of speed. And also companies can buy different wavelengths to send their data along a shared line. So even though it's a shared line, well, you can buy a kind of unique wavelength that only your company is using, yeah, just to kind of, well, increase the speed, right, since you're not having to share. Right, and well, finally then, just a software approach, SD-WAN is sometimes used due to its cheaper price. Right, so I guess, well, here's just an example. So, well, here's the WAN. I guess, well, here we've got someone from home. Yeah, here we are. Okay, so someone from home just connecting to the network, right, via a VPN. So they're going to type in their username, password, right, then they'll be able to access, well, all of the company files, yeah, all of the, I don't know, company emails, right, the company database, etc. And then I guess if we just look here, we've got sort of what different locations, like what factory, maybe a restaurant, I guess what the data center, the primary site, yeah, maybe the office. And I guess here what they're saying, well, the WAN is also, of course, connected to the internet. Alright, so if we talk more details about, well, I guess the client-server model, right, different types of requests. So one can be visiting web pages, right, well, basically, yeah, via HTTP or HTTPS. Of course, what the S means secure. Now, HTTP, what the hypertext transfer protocol, and well, yeah, S, right, again, just secure. Right, sending, receiving emails, so we're sending emails by SMTP, and actually this one, I always forget this, maybe the simple message transfer protocol, or yeah, maybe the, yeah, I know, like send mail transmission protocol. I mean, something like that. Right, yeah. So again, yeah, okay. So if you want to see the exact one, then I guess just search right for the exact name. Right, POP3, IMAP. Well, these are going to be about receiving emails. Whereas SMTP, well, that's about sending emails from kind of one email server to another email server. So let's say, for example, yeah, right, yeah, okay. So okay, let's just do this quickly. So let's say this is us, right? This is the sort of receiver. Well, we're going to send the email, and to be honest, that's probably going to be via HTTP, especially if it's via a website. Right, let's say we're using, I don't know, Gmail, right? Someone else is using, let's say, Proton Mail. So if we're sending from a Gmail account to a Proton Mail account, well, that's going to be sent from the Gmail server, yeah, to the Proton Mail, right, via SMTP. Then let's say if the person is using, let's say like some, sort of desktop software email client, well, then it's going to be downloaded either using my POP3 or IMAP. Again, actually, all of these are all A2, so yeah, this is not really relevant. Right, transferring files by FTP are basically uploading files, downloading files. Again, if you're just uploading and downloading sort of via a web browser, well, anything via a web browser is going to be HTTP. Yeah, I guess sort of some video streaming might not be, but just regular uploads, downloads, right, it's going to be HTTP. If you've got some software, for example, a common one is, well, yeah, it's called FileZilla. So FileZilla, right, that's going to be one common FTP program. You can also get command line FTP programs as well. And that's also often used, right, right, okay, so if you've got a website, well, often FTP is used. Although, to be honest, right, there's actually better ones. So the one I use is, okay, so the one I use, I think is called SCP, like Secure Copy. And that has various advantages, like, for example, well, right, okay, so, for example, it's going to allow parallel uploads, right, things like that. Right, I guess another request, let's say requesting information from a database, and yeah, sending files to the print server. So I guess while requesting that this document is printed. Right, then if we look at the two different types of clients, so right, client architecture can be grouped into two categories. Right, thin clients, well, here little processing is performed on the client. Most of the processing is done on the server. Then the client will just display it, and the display, well, either it can be a GUI or a graphical user interface, right, or well, CLI command line interface. Right, then there's going to be thick clients, so here most processing is done on the client, and yeah, I guess the server is kind of not that powerful. Alright, so yeah, I guess just to see that, and well, yeah, so if we see here, well, here they've actually called it, well, fat client, but I mean, fat client, thick client, yeah, both, both just means the same. So hopefully people understand this diagram. If we look, well, thin client, again, what we've got kind of a, well, small, yeah, I guess kind of like a, just sort of simple device, probably just input output. Yeah, not really too much storage, right? Not too much processing. Whereas if we look at thick client, yeah, you're right. Okay. So thick client, well, here then we've got our high processing capabilities, as we can see by this, well, sort of desktop, right, tower PC. And yeah, of course, right, and yeah, okay. So because of that, well, then it means the server is smaller. Yeah, also cheaper. Right. So let's look at some of the advantages. So it's quite a lot. So thin client, well, companies can host applications on a single server. Right, then it's going to be cheaper than needing a license to install the software on every computer. So hopefully that makes sense. Yeah, just hosting the software on a server. Right, the user also doesn't have to download huge files. So let's imagine, well, I don't know, yeah, like Photoshop, right, probably, multiple gigabytes. Whereas, yeah, like an online equivalent or web page, well, that's going to be probably less than 5 megabytes. And then, well, that web page, that's just communicating with the server, and all of the processing in terms of sort of, yeah, rendering the image effects, yeah, things like that, well, that's going to be done on the server, or, yeah, rather than our device. So I guess, yeah, because that was going to save storage space, I think that's kind of what we mentioned, right? Okay, so you only need one copy of the program or files. Right, can reduce, well, the administration, operation, and purchasing costs, and I think an example I saw was by 70%. I mean, that's of course going to really depend on the specific situation. Again, right, can reduce energy usage by 97%. Again, it's really going to depend on the situation. Right, updates management are easier, and this one is kind of always true because, well, here we only need to perform the updates on one server. If you have a company with thousands of computers, Well, if you had to update and well, sort of manage them, well, then of course you have to do that on 1,000 different computers. If we only need to do that on one server, well, okay. So of course that's going to be easier. Right, also less downtime because IT staff don't have to waste time fixing problems on the user PCs. Because if you've got 1,000 users, each of them have their own copies of the software, then realistically, like some of that software is going to break. Maybe the user is going to sort of modify the settings. Maybe they're going to download some virus. Maybe they're just going to mess it up some other way. Whereas if you just have one copy on the server, well, then you only have to manage that. And as long as that's working, well, then everyone should be able to access that. Right, I guess more so also protected from unauthorized software or viruses because again, well, as long as the server is secure, right, then I guess it can be quite safe. Whereas if you have like 1,000 users or 1,000 PCs and each of those, let's say employees, right, is just downloading whatever they want, well, realistically, so out of 1,000 people, some of them are going to sort of download some malicious software, probably by mistake, although possibly even intentionally. If for example they have some grudge against the company, or if they want to sort of take the company's data, right, and sell it. Right, so data can't be copied to a disk or saved to any location other than the server. So again, that's going to be good in terms of preventing against So preventing against kind of angry employees or like resentful employees who maybe they want to take the company data, right, then sell it for profit, or hold the company blackmail, so hold the company to ransom. And I think this one we may have mentioned already. So centralized server are easier to manage, easier to monitor. Right, setup is also quicker because again you only have to install the software on one server, right, rather than 1,000 different devices. Right, and this is also another advantage. So users can access the app, software, right, and data from virtually anywhere. So if we think about a WAN, well, if you're connecting to that via a VPN, then even kind of private company files, you can still access from any location. Whereas if you just have it on like an individual computer, well, then of course they have to be, by that individual computer. Right, then if we look at the thick client advantages, right, again, quite a lot. So, right, in this, so in this case, well, since we have a small server, well, then it's going to reduce load, right, hence the financial cost on the server, since it's offloaded to the clients. So basically it's going to be cheaper. So in some cases this is going to be cheaper, although you do have to think if you have a thick client, well, then you also need the initial hardware cost of having to buy these powerful computers. So for web, So for web servers, or I guess for anything where, let's say, the users are, not within your own company, then I guess it makes sense that actually you want the client to do that processing, rather than the server to do that processing. Again, because if you can offload that to, someone else outside the company, well, then it's going to save money for you. Right, can also provide quicker response times because let's say you're doing like video rendering. Well, you don't have to wait for the video to upload to the server, right? You don't have to wait for the sort of changes to be downloaded and sort of displayed on your device. In this case, since you don't have to wait for the sort of networking, uploading and download times, then it's going to be faster. Right, so often going to allow greater customizability for individual users. So if you have the software installed on your own system, then you can probably modify that however you want. Whereas if the software is installed on the server, well, probably there's going to be more restrictions, based on how you can change that, for your own kind of preferences. Right, and I think for software developers, it's also easier to create complex programs and GUIs that run locally, rather than creating things that are running on a central server, that require sort of communication back and forwards. Alright, so if we look at file sharing, well, there's going to be two models. Right, first of all, client-server model, and I think we've seen this. So a client can request a file from a server, and then the server can send it, right, just respond. Right, then there's, peer-to-peer or P2P model. So at each peer, node or seeder can either store a whole or parts of the file. When the user is downloading or leeching, they could be downloading different parts of the file from different users, right, or different seeders simultaneously. So this can have an advantage, for example, being quicker. So let's see, the client-server model, as we see, let's see, we have So here we have many clients, but basically they're all just communicating kind of one-to-one with the server, just direct communication. Right, in contrast, if we look at peer-to-peer, so here I guess we can say there's multiple seeders, I guess, sources of the files, and each person can be sending different parts of the file. So I guess if we look at this one here, so here I guess we've got, this one, and this one. right, they're all sending different parts of the same file. Yeah, therefore we say, well, this person here, right there, okay. So this person is kind of downloading multiple parts of the file, right, from different people, right? Therefore, that can be faster. Although actually, if we look at this one, actually, yeah, okay. So I think there's a small mistake. So actually, this one here, right, well, 1 and 2, right here, they're actually downloading. But if we actually just look at the direction of the arrow, right, okay, this one they're actually sending to someone else. So that's going to be another point. Well, peers can both download, right, leech, and upload, well, seed or send, right, simultaneously. Right, so let's look at the advantage then, client server. Right, so one, we're guaranteed to be able to get the whole file, because if we have sort of, well, yeah, right, okay, so if we have a sort of reliable, reputable server, well, then that's going to store the entire file, and if we start downloading it, well, then we're going to know that we can finish it. In contrast, if we just go back here, well, let's say, for example, this person has only downloaded, like, let's say 40% of the file, right? This person has downloaded, let's say 50% of the file. Well, then there's going to be 10% of the file that no one has. And in reality, like, probably these people, probably they have, you know, the same 40% or the same 50%. So yeah, this can actually be a problem where sometimes your download can get stuck, right? For example, at like 99%, because no one on the network, or at least, well, no one currently online has that remaining 1%. Yeah, whereas the client server model, well, since it's stored on one server, well, of course, that server is going to have the entire file. Right, so it's going to be easy to set up and manage. So for example, yeah, adding, deleting, renaming, copying files, since they're all stored in one place. Right, less viruses. So if downloaded from a reputable company, then I guess you can be fairly confident, you know, that the download will be safe. Right, the user doesn't require additional software, whereas if we think, well, peer-to-peer, yeah, you're going to need some program, for example, BitTorrent, or yeah, various others. And I guess, well, these, okay. So some people say the client server is slow. Although, for example, at university, well, we could download 1 gigabyte in 20 seconds. So yeah, I think the whole client server model is slow is, you know, not really an issue. Yeah, when again you think about, well, fibre optic, you know, 100 gigabit per second connections. Right, then we look at peer-to-peer. So peer-to-peer, well, can be faster. Again, I've put that in orange, you know, because of the previous reason. Yeah, client server can also be fast. Although I guess if you have, let's say, you know, 5 people all sending, you know, super quickly, well, then in that case, peer-to-peer would be faster. Yeah, because, well, you get the simultaneous streams. Right, also you can have multiple copies on the same file, kind of distributed across multiple different devices. So that's going to be, I guess, well, right, yeah, okay. So in some ways that's reliable, because let's say if you have the client server model, and if you have one server and that one server is, you know, sort of down, or yeah, I don't know, yeah, okay. So maybe the server is down, maybe the company doesn't exist anymore. Well, then you're not going to be able to access the file. However, in this case, if you have a popular file, well, then many people will have it. The kind of alternate to that is, well, if you have a file that, let's say, only one person has, if that one person isn't online, well, then you're not going to be able to download the file from anyone. So yeah, then the file is just, you know, not available at all. Right, and I guess also, well, more anonymized, right, more private, yeah, for downloaders, leechers. And I guess that also has, well, yeah, right, yeah, okay, so some advantages, some disadvantages. Also, well, more, yeah, right, okay, so I guess we can say, well, privacy is higher, but then because privacy is higher, well, that means you're going to get more illegal content, right? You know, more people sending malware, because of course, if you're sending malware and like no one knows who you are, well, then you're going to feel safer. Whereas if, for example, you have, you know, sort of a normal server, well, I guess, yeah, that's kind of less safe to send malware, because, well, potentially, right, if people find out who owns the server, yeah, then of course you can get arrested. Alright, so actually, yeah, this is the disadvantage. I think we've kind of said this, right? So if no one's actually seeding, then you won't be able to download the file. Yeah, this one, right, so if users only have part of the file, then I guess maybe you can't download the complete file, right, e.g. download stock at 99%. And well, higher anonymity, right, potentially means, well, more malicious files, right, more viruses, yeah, more illegal content, right, piracy, etc. Alright, so if we go on to the next part, where it's going to be communication system requirements, and there's going to be, well, 5 requirements for digital communication systems. Right, the first one, well, there has to be a sender. I think if there's a sender, well, there also has to be a receiver, right, otherwise you're just sending it into, you know, empty space. Right, there has to be a transmission medium, for example, Wi-Fi, twisted pair, coaxial, fibre optic, right, satellite, yeah, etc. Right, also, of course, there has to be a message, right, so actually data that you're sending. And finally, well, there has to be a protocol, well, so yeah, some of these, right, as we mentioned. And the reason there has to be a protocol, okay, so let's actually give a definition for a protocol. basically it's going to be a set of rules that are used to allow the sort of successful communication between devices. Because what a protocol is going to define, basically it's going to define the format of data. So let's say, for example, IP. Well, let's say an IP packet. What's we going? Okay. So an IP packet. Well, there's going to be the header, right? Then there's going to be the data or the payload, and then I guess there's also a trailer. Although technically the trailer is actually not sort of in the IP section. I think the trailer is going to be in the Ethernet section. So let's say that the payload, the trailer, and obviously the header. Now, obviously, what we think, the header, it's going okay. So in the header, there's going to be the source IP, also the destination IP. If you're using TCP, there's also going to be the packet number, and the packet number, that's used for reordering the packets, if they arrive in the wrong order. Also for kind of resending packets that don't arrive. Right then, of course, it's going to be the payload, right? Okay. So then there's going to be the trailer. So basically, one, we have to ensure the data is in, the sort of the correct format, the correct order. And for example, let's say, So let's say, for example, an IP address. Well, if it's an IPv4 address, then of course it has to be 32 bits. If instead we were using like 33 bits, then of course, the sort of data is going to get all skewed. The receiving device is not going to be able to interpret that properly. So hopefully that makes sense. What a protocol is basically just defining the, let's say, sort of data format, and also the sort of messages that have to be sent, right, to allow the sort of successful communication, right, between devices. Alright, so I guess, just some pictures of these. Hopefully everyone knows these, right? Wi-Fi, coaxial, fibre optic, twisted pair, and satellites. Right, then if we look at transmission mode, so data can be sent via the medium in 3 different ways. So first, simplex, data flow in one way only. Half-duplex, data flow, bidirectional, but not simultaneously. So I guess, they can send both directions, right, but not at the same time. And then, full-duplex, so data flow can be, bidirectional, both directions, right, and simultaneous. So I guess, just to see that, here we see simplex, of course, okay. So here they're saying what the, mainframe or server. So this server can only send, to this monitor. And I guess, since it's a monitor, right, that's going to be a thin client. Whereas, the mainframe, that's the sort of, big server. Right, half-duplex, of course, we see both of those, although I guess only one wire, right, so they can only send sort of, one direction at the same time. Full-duplex, actually full-duplex, okay, so full-duplex, usually there's going to be 2 wires. Of course, one wire for one direction, one wire for the other direction. Right, then there's also, 3 more. Right, it says, unicast, so that's, one-to-one communication. Right, then multicast, so a targeted signal from one source to multiple destinations. And finally, broadcast, so signal sent indiscriminately, right, anyone who sort of tunes in, can listen, right, e.g., TV, radio, that's going to be broadcast. Because anyone with an antenna, right, can then listen to that. And hopefully this makes sense. Unicast, obviously, to one device, right, multicast, to several devices, broadcast, right, just to everyone. Right, then if we look at some of the common devices on the network, so hubs, that's going to receive a message and broadcast them to every device on the network. And because of this, because it can only broadcast, this is why hubs are generally not used anymore. Right, the kind of new version of a hub, it's going to be a switch, basically it's going to do the same thing. So it's going to receive the message, right, send it to others, but this time it can send, unicast, multicast, and broadcast. So basically, okay, so a switch basically is just an improved hub. Just since it supports those 3 transmission modes. Right, routers, so, right, okay, so that's going to forward packets onto the next device, onto the next hop. And the way it's going to determine who to send it to, or what device to send it to, that's going to be based on the IP address in the packet. And then it's going to sort of look up that IP address in the routing table, and obviously, see, right, who it's going to send it to next. And I guess okay, so if we're talking about packet switching, packets are going to be sent, from one router to the next router to the next router, like many hops, and eventually they're going to arrive at their destination. Right, bridges, so they're used to join 2 separate networks of the same protocol. Right then, I think finally gateway, that's going to be the entry and exit point of a network. It's going to convert data from one protocol to another. And actually, for example, if we, okay, so again, if we talk about a home router, a home router is actually going to do, let's say, the sort of functionality of all of these. Also, for example, a DNS server, a DHCP server as well. And the reason for that is because, if you're a home user, right, a home user is not going to want to buy, 6 different hardware devices. They're going to want all of that functionality, built into one device. just for simplicity, yeah, and also cost. Alright, so then if we talk about the network topologies, right, so topology refers to the physical and or logical layout of a network. Right, I guess before we need to know one point to point, so yeah, one device directly to another. Obviously bus, central bus line, right, all devices connected to that bus line. Right, star, so a central switch, central router, right, all devices connected sort of via that. Right, mesh, so I guess, almost like point to point where each device can be connected, right, to each other, right, either full or partial. And then hybrid, so again, even though it says 4, the thing is, a hybrid is just a combination of, one of these others. So maybe we have a bus network, and then coming off of that bus network, we have, individual star networks. Alright, so let's just look at these, right, point to point, yeah, we said, direct connection between two devices, right, could be connected, twisted pair, Wi-Fi, fibre optic, etc. Right, transmission, it can be any of them, right, simplex, half-duplex, full-duplex. Right, however, since there's a direct connection, the message can only be unicast, because if we think, it can't be multicast, it can't be broadcast, because, there's not multiple devices to send it to. Yeah, there's only one, one device we can send to. Right, so the advantage is point to point. I guess, the obvious one's secure. Right, eavesdropping is hard or impossible. Hence, we can use this to connect critical or specialist servers together. Let's say, for example, we have a database server and a file server, right, generating financial reports in a bank. Well, we can directly connect those servers together, right, via point to point, rather than, let's say, having them connected on like a central bus line where anyone can actually see the data going back and forward. Although, of course, okay. So, although we say that on a bus, but of course, the data on a bus network should also be encrypted. So yeah, while it is encrypted, it's still kind of okay. So even though it's encrypted, people can still kind of see how much data is being sent, when data is being sent. Of course, if people get access to this private key, okay, so then they can decrypt it all. But anyway, back to point, so it's also fast and reliable because, dedicated connection, right, hence there's no collisions, right, no interference, no congestion. Right, however, disadvantages, it's not general purpose. We can only use it to connect two devices, which, if you think generally, that's not really kind of useful. Let's say if you're talking like a home router, probably, okay. So unless you only have one person and, one device, then that's not really going to be, realistic. Because, okay. So most routers, right, most, home routers, you're going to have, multiple devices, multiple people. And alright, so yeah, I guess this one's kind of in contrast to the last one. Now, if okay. So let's say if this dedicated connection is working, then it's extremely reliable. However, we also do have a single point of failure where if this central connection stops working, then we have no redundancy. Although the thing is, if that central connection does stop working, then it's going to be obvious what the problem is. Of course, we should be able to just get a new wire, and then hopefully it should start working again. Right, and it's also expensive because you're going to need a dedicated connection between the device. Right, then if we look at the bus, so what's going to be a linear topology, so like a line, right, in which the ends do not rejoin and are terminated with a terminator. Right, the terminator basically is going to be just a resistor. So the electrical signal is going to hit the terminator, right, then just be absorbed. Right, messages have to be broadcast along the line, so anyone can listen in, although again it should be encrypted. Anyone can intercept them. Right, and okay, so I guess encryption, although if someone does get the private key, then they could decrypt. Although even if they don't have the private key, again, they can still see some sort of metadata, like sort of the times that people were communicating, when the devices, okay. So I guess when the devices were communicating, how much data they were communicating, sort of various indicators like that. Alright, obviously just a picture, so hopefully that's fairly obvious. The central bus line here in the middle, where is it? Okay, so this one, right, the central bus line. Right, then obviously, just the individual connections are coming off, right, connecting these devices. Obviously here the black circles at the end, right, just representing the terminators, the resistors. And if you don't draw those, black, okay. So if you don't draw those black circles, right, not black lines, if you don't draw the black circles, then you actually won't get some of the marks. So when they ask you to draw a bus topology. Right, again, let's look at some of the advantages. It's going to be semi-resilient because a fault in a node or a link connecting a node to a bus won't prevent communication between the other nodes. So that's saying, for example, where's the pen? Let's say this one. Now, if this connection breaks, let's say if this device wants to communicate with this device, while this connection here actually has no effect on that. So yeah, in that case, that's why it's semi-resilient. Although, of course, the problem, well, let's say if this central bus line breaks, here we go. So if this central bus line breaks, well, then the whole thing just, stops working. Right, it's going to be relatively easy to implement. Right, it's fairly simple. Right, it's also going to be, sort of fairly efficient for small networks. Right, okay, so less network cable is required. Okay, so therefore it's also going to be cheaper. It's also going to use, less power, right, compared to, for example, star or in particular, mesh, right, full mesh networks. But it's also easy to expand because, we have the central bus line, right, then just connect an extra device to that central bus line. However, disadvantage is, it's going to be slow for large networks since each additional device slows the network down, and that's going to be because of collisions, right, since they're broadcasting, then if someone else is sending, right, the device that wants to send has to wait for the other people to stop sending, right, before it can then send its own data. Right, potential for eavesdropping because, okay, so again, since the data is broadcast along the public bus line, although, encryption, it shouldn't be too much of an issue. Right, identification problem can also sometimes be difficult if there's a problem in the central bus line. Because I guess if you have, let's say, a long bus line, right, maybe it's like 100 meters, you don't exactly know the sort of specific point of, where the connection is for. Okay. So you don't know the specific part of the wire that's broken. Whereas I guess something like a star topology, then it's going to be simpler, because basically you've just got kind of like a one-to-one connection, right, from the device, to the central, okay, let's say from the device, right, to the central switch, for example. Right, and also, chance of collisions, right, hence the packet loss is high, right, and, the data is slow. Right, then if we look at, the mesh, right, in particular the full mesh, right, so each node has a point-to-point connection with all the others. Right, transmission, it's usually going to be full duplex, and messages can also be sent, unicast, multicast, broadcast. And if we think about that, that kind of makes sense, right? Let's say maybe this one wants to send to this one, that's going to be unicast. Or for example, wants to send to this one, and this one, or of course we can send, broadcast, right, to everyone, just by sending out, the various point-to-point connections. Right, and also if a connection is unavailable, the message can be, let's say routed, right, along another path. So if this one wants to communicate with this one, if this, okay. So if this line is down, then of course it can send right via here and then via here. Just to do that. Right. However, okay. So I think we actually saw the formula for this in the sort of full video. If we have, let's say, like 100 devices, that's going to mean probably thousands or like tens of thousands of different wires will be required. So realistically, we don't really want to connect every single device. So because of that, then we can use, say, a partial mesh. So we might have some important, okay. So let's say we have some important devices like a server, for example, a database server, email server, a web server. Maybe then we want to connect all devices to that. But let's say if we just have like some individual computer, we probably don't need, the individual computers to be connected, right, to every other individual computer. So partial mesh, we just connect the devices to the important ones. And I guess, the sort of, less important devices, they don't need a point-to-point connection, right, with all the others. Alright, so let's look at the advantages. It's going to offer full duplex communication, right, of course, fast, sort of, reliable. Right, so it's going to offer, all three transmission types, right, unicast, multicast, broadcast. It's going to support high traffic load, and again, that's because you've got the direct connection. I guess, multiple devices can transmit data simultaneously across different wires. Right, resilient because, if one of the sort of wires breaks, then you can, of course, reroute a different way. Right, so more advantages, high privacy security because, dedicated connections. So if you're sending, let's say, from A to B, then, of course, device C is not going to be able to listen into that, compared with, say, the bus topology, right, where, of course, it's sent publicly. Right, also adding additional devices doesn't disrupt data transmission between the current devices because, let's say, if we have, 3 devices, if we then want to connect a 4th device, then we're just going to add that, and of course we just sort of add connections, right, to those 3 existing devices. We don't have to sort of reconfigure the network or, turn devices off. Right, for identification is also easy since you know exactly what line is down. So if from A to B is stopped working, then of course that's the connection that's broken. Right, I guess also no centralized authority. So that can also be good in terms of like privacy, for example. Right, have some disadvantages. One, expensive, right, large amount of wiring. I guess also unrealistic. Right, building and maintaining is going to be extremely difficult, even with a relatively small number of devices. Certainly, again, if you start talking about, let's say, 100 devices, well, as mentioned, you're going to need sort of like tens of thousands of different wires, tens of thousands of connections, which is just okay. So obviously, okay, so that's not really practical. Right, high power consumption again. Well, lots of wires, right, lots of data being sent. Right, could have redundant connections, even if a partial mesh is used. So maybe you sort of have a connection from device A to device B, but maybe that doesn't actually send much data. So I guess you also have to kind of monitor this, quite frequently, to check, well, do you actually need all these connections, or could you remove some of these to save money, for example. Right, then if we look at topologies, so we have a central switch that all, well, I guess all devices or all sort of packets go through, right, to communicate with the others. Right, switches, well, again, it's going to support unicast, multicast, broadcast, and that kind of makes sense because, well, let's say, right, this device can send to the switch. Now, if it tells the switch to send to everyone, well, then, of course, the switch is going to send to everyone. Right, if it tells the switch to send to, okay. So if it's, if it tells the switch to send to the device with, let's say, this MAC address and this MAC address, well, then it's only going to send to them. And that's going to be based on the port. So that's going to be used the MAC address table. Okay. So hubs only support broadcast. That's why generally we're going to use a switch instead. Although okay. So as mentioned in this diagram, well, so it could be either a hub or a switch. Although realistically, right, 2025 is probably going to be a switch. Right, so switch will support a list of okay. So usually it's going to be the MAC addresses. I mean, it can also be IP addresses. So packets can be sent to the correct device. Now, if it's a LAN, right, then it only has to be the MAC address. If you're, for example, using a switch to connect, right, let's say different networks together, then I guess it can also store the IP address. But I think switches, there's actually sort of different types of switches. Although I think generally, if you say sort of a common use, well, it's just going to be the MAC address, right? Since it's going to be on a LAN. Right, and the star topology, well, this is the most used in practice, and if you think about this, well, this is actually what your home router is. So if you remember, well, even though we call it a router, right, your home router also has the function of a switch. Let's just say router. Although in the exam, okay, you'd want to say switch, because actually, if you're talking about just on a LAN, well, then all you need is a switch. If you remember, well, a router, that's going to be about sending packets outside the network. Of course, well, to the next hop. So if you think about this though, well, this is basically how your home router is working, where you've got the central router, and then of course okay. So each device is then just sending data to the router, right? That router can then send it to other devices on the network, for example. Although again, right, in the exam, right, probably say switch. I only say router because, well, that's probably what people call it, when talking about their home router. And that's what we're just saying here. Alright, so the advantages, well, it's going to offer full duplex communication again, 3 transmission types, right, unicast, multicast, broadcast. Right, so due to the node, so due to the hub node connections, having point-to-point connections, there's going to be no collisions. So I guess that also makes it fast. Right, each device only needs, one I/O port, right, one input-output port, right, to connect to the switch. Whereas if we think, let's say, a mesh, well, if it's connected to 5 different devices, well, then you're going to need, let's say, 5 Ethernet ports. Right, it's going to be relatively easy to implement. I guess everyone is familiar, probably setting up their home router, right? Just plug it in, type in the password. There's not really too much configuration. Right, it's also easy to identify the fault because, you have the point-to-point links, between, okay. So point-to-point links, right, between the hub and the nodes. And again, actually, rather than saying the hub, I guess you say switch, so switch and nodes, or the central device. Also resilient due to the point-to-point links, unless the central switch goes down. And of course, if the central switch goes down, right, same as the bus network or bus topology, if that central line, or if here the central switch goes down, well, then the whole network just stops. Right, so I guess that's the disadvantage, right? If the central switch fails, right, the whole network fails. Right, I guess more expensive. Right, okay, so more expensive, more cable than bus. However, of course, less cable, right, therefore cheaper than the full or partial mesh. Right, the switch can be under high load in a large network, right, therefore, of course, that's going to slow down. Right, extra hardware, so switch is required compared to the bus topology. Although I think that's not really an issue because, well, if you think a switch, right, a router, yeah, that's, you know, super cheap usually. Probably what, just like, I don't know, like $20, right, something like that. Right, performance also depends on the switch. So if you have a good switch, right, high specifications, right, high throughput, then I guess it's going to be fast. If you have, let's say, a cheap switch with, I don't know, let's say like 20 different devices connected to it, yeah, in like a classroom or an office, well, then of course, yeah, potentially it can slow down if they're all, you know, streaming HD video, for example. Right, so finally then, we're hybrid networks. So I guess we can just, yeah, create a network with multiple topologies, right? This will be a hybrid network. And hopefully we can see this. Well, here we're going to have what the yeah, right, yeah, okay, so actually this is not really the best diagram, because I guess we've got the sort of central bus line, right? Then we would probably want to draw the devices coming off it like that. But yeah, hopefully you can still see how this is kind of a bus line. Yeah, then just what these star topologies, or yeah, the star networks, kind of, you know, coming off of it. Yeah, like here, for example. Alright, so I think, yeah, the transmission media we kind of mentioned briefly, right? So we're wired, right, twisted pair, coaxial, fibre optic, right, wireless, well, Wi-Fi, satellite, yeah, Bluetooth. Bluetooth is not really mentioned much in the exam, although, yeah, maybe they might mention it one time. Right, so key terms, well, one, bandwidth, that's a measure of the amount of data that can be transmitted per second, right, usually in, well, megabits per second or, well, gigabits per second. So you can think of this sort of road analogy, where let's say here on the left, okay. So if we assume that all of these are going at the same sort of physical speed, well, here I guess, well, this has sort of like 1 car per second, or yes, or 1 car, you know, at the same time. Whereas, okay. So here, of course, there's 4, right? Therefore, this is going to be faster. Right then, attenuation, so that's the rate at which the strength intensity of the signal decreases. So in this case, I guess this is kind of quite low attenuation, at least we're kind of starting at the top. So if, for example, we have something like that, well, that's going to be high attenuation, right? The signal strength is decreasing in intensity quite quickly. Whereas if we have something like this, well, this is going to be quite low attenuation, right? The signal intensity is, you know, decreasing quite slowly. And actually, right, for bandwidth, yeah, right, yeah, okay. So bandwidth, I think I said faster. I think faster is not necessarily the word you want to use because, well, you might think faster is in the sort of physical speed. Basically, it's the amount, right? So yeah, I think that's the keyword. Yeah, right, yeah, okay. So it's going to be the amount of data. And yeah, right, okay. So I think let's talk about that in more detail. So let's think then, what factors are going to affect the bandwidth? Well, one is actually the physical speed of the data transmission. So for example, the speed of each car. Now, if you think fibre optic, well, fibre optic, that's using light, and what light is, what, 3 times 10 to the power of 8. And what is that going to be, meters per second? Yeah, I assume. So yeah, that's going to be extremely fast. But even, for example, electric signals, now I think electrical signals is also 2 times 10 to the power of 8. So in effect, what they're both, what sort of, okay, so what, 300 million meters per second, and what, 200 million meters per second. So in reality, right, there's actually not much difference. Right, the main difference between, well, fibre optic and electrical signals, for example, like, well, twisted pair, right, coaxial, it's going to be the frequency. So the frequency are basically kind of the distance of one car to the next. So if we do a side-on view, well, let's say here we have one car, right, then here we have another car, here we have another car, here we have another car. Right, of course, well, that's going to be an extremely sort of, well, high bandwidth. Yeah, we're sending lots of data per second. If in contrast we have a low frequency, well, let's say here we have one car, right, then here we have another car. Well, of course, okay. So this then is going to be low bandwidth because, well, the cars are kind of far apart. So that's actually why fibre optic is a lot faster, because fibre optic, well, light is going to have a much higher frequency, right, compared with electrical signals. I guess, yeah, also, well, the number of channels, and if we think about cars, well, that's basically how many lanes there are. So, well, 1 lane on the left, right, 4 lanes on the right. Yeah, if we look at, you know, this example here. Yeah, right, so I think we sort of mentioned that already. Right, if we think, well, what factors affect attenuation? Right, so one, the substance the data is transmitted through. So, well, copper, air. Obviously, well, buildings, walls is not going to be very, you know, efficient to go through. Yeah, rain, vacuum. Yeah, so I guess if we're talking about, right, okay, so if we're talking about electromagnetic signals, well, then I guess, yeah, a vacuum is going to be good, because, well, basically there's no sort of particles for them to collide with. Yeah, nothing to kind of like reduce the intensity. Right, also the frequency, so low frequency waves, e.g. radio, they're going to attenuate less than high frequency waves, for example, gamma waves or rays. And that's why, of course, while radio signals can be, sort of detected like kind of even the other side of the world. Whereas, yeah, gamma, I mean, that's going to get blocked quite easily. Right, then if we look at one of the transmission mediums, right, so twisted pair, well, there's going to be insulation and shielding. And if we see here, so I guess in this case it's kind of like a rubber shielding, or like a plastic sort of rubbery shielding. And I guess most people are familiar with this, right, actually. So a lot of people call twisted pair just like an Ethernet cable. Now, technically, Ethernet is the protocol, right? Twisted pair is actually the name of the cable. But I think most people have probably seen, twisted pair cables, and if you feel it, what it's like, well, sort of, yeah, like a plastic, right, rubbery kind of coating, or shielding insulation. Yeah, and I guess if we look here, so yeah, we see what rubber. They also say, I guess, well, copper. Yeah, okay. And also, well, the twists are also used to reduce the electromagnetic interference. Now, if you want to see that, I mean, you can just search, why are twisted pair cables twisted? I also mentioned that in the other video. Although, yeah, this video we're not going to mention it, right? It's kind of, yeah, okay. So it's beyond the sort of scope of the syllabus. Alright, twisted pair, so advantages, well, one, basically it's cheap, that's really the only advantage. Here I'll put in orange because, well, even though it's lower bandwidth compared to coaxial and in particular fibre optic, the bandwidth is still extremely high. And I think twisted pair you can get up to, let's say, 100 gigabit per second. So if you're just talking about, let's say, home or office connection, well, that's still going to be, sort of more than sufficient. Okay. So it's going to be sufficient for, let's say, a home office connection. If you're thinking about using it for sort of the global undersea cables, which like millions of people are going to be using, well, then of course it's not going to be fast enough, or yeah, the bandwidth is not going to be high enough. Right, that's why you're going to need, well, for example, twisted pair. Right, okay, there's also relatively high attenuation, and I think it's something like maybe 30 or 40 meters. After about 30 or 40 meters, right, twisted pair cables generally are not going to work unless you have a repeater, right, just to boost the signal again. We're also strongly affected by interference. Of course, yeah, the twists do reduce that, although, yeah, I guess not that much. Okay. So not as much as, for example, fibre optic. And I think fibre optics, they can go maybe like 1,000 kilometers, right, without the need for a repeater. Yeah, whereas twisted pair, I think only maybe 40 meters, right, before they need a repeater. Yeah, because of the high attenuation. Alright, so again, yeah, that's relative, and I'm going to skip that, although if you want, you can pause, right, just read that. Yeah, just to keep the video a bit faster. Whereas the coaxial, well, again, it's going to contain insulation to reduce interference. Yeah, as we can see, I guess, well, yeah, the outside insulation. Also, well, the kind of inner insulation as well. Alright, so 2 levels. Yeah, okay. Right, so okay, so it was mainly used for old broadband connections, so yeah, kind of old internet connections. I guess, yeah, also old TV, old radio. I think apparently it's still used sometimes in CCTV, right, so cameras. And I guess that's because, well, you have a faster connection, or yeah, so, right, yeah, okay. So again, let's not say faster, okay, let's say higher bandwidth connection, right, compared with twisted pair. Right, let's look at, well, again, advantages, disadvantages. So actually, coaxial is quite easy. Basically, it's in the middle. And actually, I think all of these are quite easy because, well, twisted pair basically is the worst for everything but the cheapest. Right, coaxial, well, it's in the middle, but yeah, again, sort of the middle price. And then, well, fibre optic, basically it's the best for everything, right, but the most expensive. So coaxial, well, moderate cost, moderate bandwidth, yeah, moderately affected by interference. Right, moderate attenuation, yeah, and I guess, well, sort of, yeah, moderate number of repeaters. And if you think, well, the number of repeaters is, related to the attenuation. So if the signal strength decreases quickly, well, then you're going to need more repeaters, right? If the signal strength decreases slowly, well, then of course, okay. So then of course you're going to need, you're going to need less repeaters. All right. So actually, the book says coaxial has the highest attenuation, although when I actually searched online, for example, from cable manufacturers, yeah, they were saying twisted pair has higher attenuation than coaxial. So to be honest, I think probably I'm going to trust the cable manufacturers, yeah, rather than what the book says. Right, then finally, well, fibre optic, so light transmitted at high frequencies through glass tubes, and again, high frequencies. All right, this is actually why the bandwidth is so high. Right, I guess current world record is, well, 1 petabit per second. Right, current commercial solutions about, well, 100 gigabits per second. This was made sort of, well, maybe 3 or 4 years ago. Maybe now it might even be faster than that. Right, okay, so the bandwidths, okay, so the bandwidths are per glass fiber. So if, for example, we look at this picture, well, here we have, what, maybe about 10 glass fibers. Yeah, if we look at, all these individual tubes. So if each one is, 100 gigabits per second, well, then, of course, that's going to be, 1 terabit per second, yeah, if there's 10 of them. Right, fibre is also less affected by interference. Again, okay. So again, as we said, it's going to be the most expensive, right, but the best for everything. Yeah, okay, all right. I think that's fine. All right. So as mentioned, high bandwidth, right, low attenuation, right, low need for repeaters, least affected by interference. However, disadvantage, right, expensive. All right. Okay. So also this is going to require specialist equipment. And I think generally it's also going to require sort of more specialist sort of expertise to actually set this up. So I think if you're like a sort of a maintenance person, then, or kind of like an engineer, right, then I think it's easier to set up, let's say, twisted pair coaxial, right, compared with fiber optic. All right, so let's think, why doesn't everyone use fiber optic? And basically, again, as we can think, if you're talking about home or small office use, then you don't really need, 100 gigabit per second, right, per glass fiber. So if we think twisted pair, okay. So here it says twisted pair supports 40 gigabits per second. I think maybe now it might even be 100 gigabits per second. So if you're talking, okay. So again, for home small office use, right, that's good enough. It's only really going to be huge companies, ISPs, that are going to need, fiber optic. For example, the undersea cables. All right, and here's just a comparison of all of that. Again, if you want, pause the video, although I think, we just mentioned that already. All right, so then Wi-Fi, I guess, for the wireless communication mediums. Right, so it works by transmitting data over radio waves. Right, different channels, right, different frequencies are used to reduce interference. So let's have a look at that. Now, if, for example, here, I guess, here we're saying what we're kind of sending data on by a similar frequency. So then what you can get, then you get this interference. Right, so in order to fix this, then we're going to use different channels. So let's say here, for example, we see the first channel here. So I guess we're saying, some devices will be sending on this channel 1. Obviously, yes, some devices can be sending on, for example, channel 2. And I think actually they're saying what channel 2 is this green one. So basically you just have these sort of different frequency ranges. And then, because they have different frequency ranges, then you're going to get less interference. And probably there's going to be some sort of signal processing at the end that it can probably sort of eliminate the interference, based on probably sort of like Fourier transforms, or yes, okay, so okay, so probably something like that. Right, so bandwidth utilization is also increased because rather than having everyone send on the same channel, which again we're going to get interference, right, people are going to have to wait. Here, if we have 10 different channels, then effectively we can have sort of 10 different devices sending simultaneously. Right, then if we look at 2 different types, so guided media, that means we can kind of aim the signal, and when we say aim, that's talking about the sort of physical, I guess, sort of like the angle, right, the angle of the signal. So I guess guided, if you think about the sort of angle that it's going to go, basically, okay, so we're basically going to have a kind of like low angle that it's going to spread out. Whereas if we think unguided, I guess the ultimate unguided, it's just going to be 360. So it's going to, okay. So I think something like radio waves are just going to be like that, where radio waves are just going to kind of emanate or emit, right, in a sort of 360 degree radius, kind of spherically. And I guess by definition, cable is going to provide a one-to-one connection, right, hence a guided, right, unguided by signal sent in all directions, e.g. wireless access point. So again, wireless access point, that's built into the router. Radio tower, TV station. And if you think, a radio tower and TV station, actually they have to send the signal in all directions, since of course, you're going to have people in all different locations, right, trying to actually access this. Alright, so let's say, remote control. So remote control, that's going to use infrared. And if you think, if you don't aim the remote control kind of, let's say, sort of, directly or fairly directly at the receiver, then it's not going to receive it. Like if you aim it, let's say 90 degrees, from the TV, then the TV is not going to, intercept that signal. So what we could say then, electromagnetic waves with higher frequencies are more guided than those with lower frequencies. Right, that's why radio waves are going to travel kind of spherically, right? Since radio waves have low frequency. Okay, then if we just sort of have a comparison of all of them, so if we say, so as we increase the frequency, well, then the bandwidth is going to increase. And as mentioned with the car example, that's because, well, if we have a high frequency like this, then let's say, for example, so let's say the peak represents a 1. Then let's say if we have a low frequency wave like this, let's say what a 1, and then maybe obviously another 1 here. Well, hopefully that's fairly obvious, sort of graphically, that if the peaks and troughs are closer together, well, then we can, just send more data per second, right? So therefore the bandwidth is higher. Right, however, the attenuation is going to be higher, right? The higher frequency. So something like this, okay, this is going to attenuate quite quickly. Whereas something like a radio wave, well, a radio wave is going to kind of lose signal strength quite slowly, right? Therefore, a radio wave can travel a longer distance. And here it says most of the attenuation is due to rain. So I guess, just sort of things in the atmosphere, like rain. Right, I guess need for repeaters. So because it, so because it attenuates more, therefore we need more repeaters. Right, so high frequency means, well, we can sort of have a higher directional focusing capability. So we said, what a remote control, we can directly focus, whereas something like radio wave is just going to be sent in every direction. Right then, penetration through a wall. So I guess the same way, a radio wave is going to sort of penetrate less through a wall. Okay, so and then what interference, right, there's no trend. Alright, and I guess if we talk about 5G and 4G, well, 5G has a high frequency, right? Therefore, that's why we're going to see, these traits. So 5G, right, therefore has a higher bandwidth, right, but a shorter range. And I think actually 5G is more likely to get blocked by walls. Okay, so actually I think this one I got a bit confused about. So here, if we're saying the penetration through a wall, well, this is better. So here we're saying, well, radio waves can travel through walls, whereas, for example, 5G, this is why actually if you have a router that's, a 5G and 4G setting, well, if you're close to the router, you can probably use a 5G. However, let's say if you're in like a different room, or if you're, upstairs or something, well, then maybe you want to use the 4G connection, because, the 5G connection is not good at, traveling through the walls. Right, so just about advantages, and I guess really this is talking about, wired media generally. So it's going to be accessible with portable devices like laptops, tablets, phones. No cables required. And if we think, well, let's say a phone, I mean, you don't exactly have like an Ethernet port, on your phone, or like a twisted pair port on your phone. Right, I guess setup's also easy, fast, and right, suitable for public locations, right, cafes, hotels, transport. Again, of course, because you don't need cables. It's not really realistic to have, let's say a hotel which has hundreds of cables for people in the restaurant. Right, however, disadvantage, well, it's going to be lower bandwidth compared to cabled, wired methods. Right, also less secure than wired methods because anyone can listen in, although again, data should ideally be encrypted. Right, also a high absorption rate, e.g., blocked by walls, and right, short range. So I guess Wi-Fi, right, 20 to 150 meters, and I think for a home router, I mean, probably 20 meters is sort of like the maximum, to be honest. Right, so satellites, well, it's going to be 3 different types of satellites, right? Geostationary, that's going to stay above the Earth in a fixed position, and only 3 of those are required for the whole Earth coverage. Right, medium Earth orbit, provides, let's say, GPS. I guess that should be a big S, right? GPS. Right, 10 here are going to be required for whole Earth coverage. Right, low Earth orbit provides the mobile phone network, and 50 are required for full Earth coverage. Right, so for example, Starlink operates at only 340 kilometers above the Earth's surface. So obviously, Starlink being Elon Musk's mobile, mobile satellite company. And if we think, what that's saying, let's say geostationary, because this is a long way away, let's say we have one satellite here, let's say one satellite here, obviously one satellite here. Well, because they're a long way away, right? Okay. So then we only need 3, right, to cover the whole Earth. Whereas if we have satellites that are a lot closer, well, then of course, we're going to need a lot more satellites, right, in order to be able to, send the signal around the entire Earth. Alright, this one, I think this is not really relevant. Okay. So as you can see, it's just in the book, although, not really in the exam. It says, right, Van Allen belts contain high levels of electrically charged particles, right, hence satellites aren't placed there, because I guess it's just going to mess up with their equipment. Right, so satellite, can act as a component in a network, right, or it can directly communicate with ground-based components. So I guess what they're saying, you could have, let's say, this ground segment here, And if this is like a mobile network, well, maybe, yeah, right, yeah, okay. So we could have it where, let's say, this ground segment, right, this like, let's say mobile tower is directly communicating with the satellite. Let's say this satellite is then, directly sending to another tower. Then of course, yeah, it can like, send the phone call. Right, or you could have it where it's going to go to this satellite, right, then it's going to go to this relay satellite, yeah, sort of higher altitude. Right, then from this relay satellite, right, then of course it can go, yeah, back to, let's say, well, this or another ground-based component. Yeah, right, so ground-based components can be further apart than a network without satellites, right, since, well, the relay satellites, they're probably going to be geostationary. Yeah, they're going to have, well, a large view of the Earth's surface. However, because of the large distances involved, well, it's going to be a higher latency, and, well, the latency, right, that's the time to receive the first byte, compared to, for example, fibre optic cables. Because if you think, well, fibre optic cables, well, that's only having to go, sort of, well, yeah, okay. So fibre optic cables is only having to go, sort of, yeah, okay. So it's only having to go along the Earth's surface or, sort of under the sea. Whereas, of course, well, this is having to go right all the way up into space. Right, so I guess because of this, right, high cost, high latency, low bandwidth, right, satellites are only used for specialist applications, right, where alternatives, e.g. fibre optics, are not available. So, for example, I guess mobile phones, well, mobile phones you can't connect to a fibre optic, right, therefore, of course, you're going to need a satellite. Well, GPS military tracking, yeah, again, should be fairly obvious, right, why they're going to need satellites, right, not wires. And also internet in remote locations, or, yeah, also after natural disasters. So I think, for example, Antarctica, I think Antarctica you can only connect via satellite. Yeah, they don't have any, fibre optic cables. I guess, yeah, after natural disasters, well, if, let's say, the ground-based infrastructure is being destroyed, well, then hopefully the satellites will still be working. And as long as, I guess, these ground segments are working, right, then I guess that's still going to work. Yeah, and I guess, well, this one, right, internet access on planes, which is becoming, right, more and more common these days. Right, so, yeah, right, yeah, okay, so I think this one we kind of mentioned, right, advantages were accessible from anywhere, right, specific use case, GPS, etc. Right, disadvantages were expensive, right, lower bandwidth, right, high latency, right, and were extremely complex. Also, repairs are difficult or impossible, because if, let's say, you have some hardware error on the satellite, well, you're not going to have a way to actually repair that. You can't sort of send someone up there to repair it. Right, then if we think about, well, local communication safe, well, for home small office use, right, twisted pair and Wi-Fi are going to be good options. I guess coaxial is fine, but I guess, right, yeah, okay, so coaxial requires hardware that's less common these days. People are generally not familiar with coaxial. And I guess for these two simple situations, well, since we don't need the high bandwidth that fibre optic provides, right, then, twisted pair and Wi-Fi, yeah, that's going to be sufficient. Right, I think we said that, well, Wi-Fi convenient, right, people can move around, right, use portable devices. Right then, well, global communication, I guess fibre optic would ideally be used, right, due to the extremely high bandwidth and cheaper price, right, compared with satellites. And yeah, right, yeah, okay, so yeah, okay, so here we're saying cheaper price compared to satellites. Now, of course, fibre optic is, well, more expensive than, well, twisted pair or coaxial. But again, twisted pair and coaxial, well, they're not really suitable for global communication. Yeah, if we're talking about global communication, well, I guess so, well, fibre optic or satellites. And yeah, right, yeah, okay, so fibre optic is going to be cheaper, right, compared to satellites. Right, I guess, yeah, so if we require GPS or remote locations, then I guess satellites have to be used. And again, this is just going to be an overview, right, just of everything. So I'd say, yeah, pause the video, have a look at this, yeah, if you sort of need to. Alright, so yeah, I guess we'll just more then. So coaxial was the most common way on a LAN, I guess, a long time ago, right? These days, twisted pair is the most common. Yeah, I guess, well, fibre optic, right, provide the backbone, right? For example, ISPs, right, the undersea cables. Right, bus topology terminators. Now, this we have actually discussed, although there will actually be sort of more new hardware as well. Right, they're going to be, well, resistors that absorb the electrical signal. Right, it's also going to stop it reflecting back down the line and causing interference. And I guess you can just see an example, right, just this metal, yeah, metal terminator there. Right, then if we look at repeater, so if a line is long, right, e.g. a bus network or long distance fibre optic cable, then because of attenuation, repeaters are going to be needed to retransmit the signal at full strength. Right, and I guess, well, remember fibre optic has the lowest attenuation. Alright, so I think here it says repeaters are only needed every 100 kilometers. Alright, so not 1,000, but yeah, I guess 100, right, still quite long. Right, so repeaters can also be used in wireless, for example, Wi-Fi phone towers. And that may be because of distance, right, or maybe because of obstacles, right, such as walls or hills. And hopefully you can see, based on this picture, if you have two people kind of, right, okay. So if you have, two people sort of either side of a mountain, right, then of course, that's why you're going to need those repeaters. And that's why, if you think about it, that's why a lot of, let's say, cell phone towers right there, okay. So cell phone towers are placed on top of a hill or, on high ground, for exactly this reason. Just so they're, less obstructed, right, by the geography. Right then, the RJ45 connectors, so twisted pair, basically they're going to contain an RJ45 connector at either end. And the RJ, okay, so the RJ45 connector, basically that's just, this end connector. The actual wire, so let's say, the wire here, this part, this is the twisted pair wire. The connector, that's just, the connector at the end. Right, okay, so one end is going to plug into, let's say the switch, right, the other end is going to plug into the device, let's say, the desktop, right, the server. I guess laptops, although these days modern laptops, right, generally they're thin. I think modern laptops generally don't have, like a, twisted pair or Ethernet port. Right, so bridges, I think we mentioned this, right, so bridge was used to connect different LANs together, right, and let them function as if they're a single network. And I guess, again, you can connect it via a twisted pair cable, right, with an RJ45 connector on the end. Right, then we say hubs, so hubs are almost never used, but I guess they might still be mentioned. And the reason they're never used, since they broadcast to all other devices. Now, in some situations that might be useful, let's say video streaming, if we have many people and we want to send this video stream to everyone, then you can use a hub. But I guess, in sort of modern, okay, so not modern, I guess in sort of normal, typical cases, right, we probably, want to have the sort of, I guess, flexibility of choosing, right, unicast, multicast, broadcast. So because of that, that's why we want to, okay, so that's why we want to use a switch. So a switch, it's going to store the MAC address, sometimes also IP address, of devices on the network. A device will send frames or packets, right, with a destination MAC address to the switch. Right, the switch will then look at its sort of MAC address table, and then it's basically going to sort of send out the correct port. So if it says MAC address, I know, AA, right, BB, obviously whatever. So right, if this MAC address is in, let's say, like port 1, for example here, then it's going to send out of that MAC address. Right, okay. Okay, so then it's going to send out of that port. If someone is sending to a different MAC address, let's say for example on this port, then of course it's going to send out of that port, right? So hopefully that makes sense. It's just kind of mapping the MAC address, right, to the to the port numbers. Again, right, supports unicast, multicast, broadcast. Right, then network interface controller or network interface card, right, NIC. Right, so the Ethernet port will be connected to the network interface card, right? That's the green circuit board in the picture. Right, so the NICs, they're going to establish the initial connection, right? They're going to handle the communication, for example, buffering, error correction, interrupts, right? Store the device's unique MAC address, right? Perform encryption, decryption, just etc. Right, then there's going to be the wireless network interface controller or card, right? WNIC. So this one's going to provide the same features as the NIC, but just for wireless communication, right? E.g., over Wi-Fi, Bluetooth, mobile networks. So again, okay. So this time it's going to contain an antenna, right, just to transmit or receive the wireless signals, right? And similar with a NIC, where it's going to establish the initial connection, right, handle communication, right, buffering, error correction, interrupts, store the MAC address, right, perform encryption, decryption, just the same as the same as the NIC. Right then, I guess wireless access point, right, WAP. So it's the central device in a wireless, okay, so I guess wireless LAN, right, just wireless network, right, that's going to be the wireless access point, right, a home router is again going to provide this functionality, it's going to receive and transmit the wireless signals, right, via the antenna or antennas. Right, if a client has a wireless network interface controller or card, right, WNIC, then it should be able to connect to the wireless access point. Right, then if we look at gateways, so it's going to act as a gate to the network, i.e. packets entering or exiting the network will pass through it. Right, can convert incoming, outgoing data between different protocols. Right, can act as a firewall to allow or block packets based on certain criteria. So I guess the gateway is also kind of like a security device as well. Right then, I think maybe finally routers. So right, technically routers only route. So I guess direct or forward packets, right, data, to the next location, right, to the next hop, the next device. Okay, so I think as mentioned many times, what people call a home router actually provides not only a router but also a switch, a bridge, right, wireless access point gateway, DNS server, DHCP server, right, etc. So hopefully we can see here in this network, thinking about packet switching, well, first it's going to send it to this router, right? This router is going to look in its, routing table. Right, based on that routing table, well, then it's, obviously decided to send it to this router, right? Obviously that sends it to that router, etc. Okay, so etc. until it, kind of arrives at the final device. Alright, so I guess everything in contrast, well, let's say you have a router at the bottom of the ocean, maybe for example like this one here in the middle of the network. Well, of course that's not going to need these other features like being a wireless access point, because if you're at the bottom of the ocean, well, no one is, connecting to Wi-Fi. So that's why, again, like when we say router, well, technically a router is only performing, this kind of forwarding packets right onto the next hop. Although, yeah, when we say a home router, like I guess really because you don't really want to be okay. So you don't really want to say, well, yeah, this device is a router, DNS server, DHCP, gateway, bridge, etc. So because it's going to be too long to say all of that, well, people just call it a router. Even though again a home router does many different things. Right, so routing tables, I think we mentioned this. So let's say device 12.0.0.1, or I want to send to 14.0.0.1. Then we just basically want to think, so we're going to start here on network 12. Then we're going to look in, network 12's routing table, of course, just determine where to send that to. Well, since we're sending to 14, right, then we're going to send it to, router 1 here. Right, if we just follow that, well, then we should get this path. Let's say if we want to send, 12, 0.0.1, right, 12.0.0.2. Well, since that's on the same network, well, then it's just going to go, let's say, to this switch. Right, this switch will realize it's on the same network. All right, then it's just going to send it, I guess, to the correct device. Right, okay, so if we think about collisions, so if we use a shared medium if we use a shared medium for transmission, right, e.g. a bus lane for data transfer, then that means there could be a collision. Right, and collision, well, that's two devices transmitting at the same time. Right, that's going to cause interference and the data can become corrupted. So an approach where CSMA-CD, carrier sense multiplexers with collision detection, can be used to solve this. And I guess here we can just see what two examples of collision. So I think they're saying actually, these two. So if we have these two waves, right, then it's going to result in this sort of big wave here. Now that's going to be called constructive interference, because they're going to kind of increase the signal. If we have the waves that in this case, they're going to be 180 degrees out of phase. So if they're 180 degrees out of phase, well, then we're going to get destructive interference, where they're just going to cancel out and, of course, create this flat line. So hopefully people can see here, I guess, what computer A, computer B, right, they're sending at the same time. Right, therefore, we're going to get a collision. We're going to get this kind of corrupted signal. Right, so let's look how CSMA-CD works then. So first we're going to, okay. So when we say check, well, that's going to be the devices are going to check. So the device that wants to send is going to check the voltage level on the wire. Right, if there's no voltage, well, then it means, right, there's no activity, no one is sending. Because if we think, well, someone is sending an So if someone is sending, well, there's an electrical signal. Right, therefore, if no one is sending, well, then there's no voltage, no electrical signal. Right, so if there is a voltage, then we want to wait a random amount of time, before rechecking. Just to sort of check, sort of if no one is sending in the future. Right, then if no activity is detected, well, then we can actually start transmission since, no one else is sending. Right, as we're sending, we're going to continuously check for collisions. Right, if there's no collision, well, then we just continue transmission. However, if there is a collision, well, then we stop transmission and we transmit a jamming signal to notify the other nodes on the network of a collision. And we're then going to wait a random time and try again. Alright, and I think this is going to ask, no, okay, okay. So let's think then, why do we want to wait so why do we want to wait a random amount of time before trying again? And the reason for that is, well, if we have two devices that sort of send at the same time, right, they cause a collision. Well, let's say if they both wait, I don't know, like 0.1 seconds. Well, if they both wait 0.1 seconds, right, then they're going to send again at the same time, right, there's going to be another collision. Right, then they're going to wait 0.1 seconds again, right, of course, they're going to send again, right, another collision. So if, for example, we have it where, let's say, I don't know, okay, so let's say this device, waits, right, 0.1 seconds. Let's say, for example, this device waits, I don't know, 0.2 seconds. Well, since this one is sending, right, this, okay, so since A is sending, well then B, right, B is just going to do what it's done before, so it's going to check the voltage. And since it sees that, well, station A is sending, right, computer A is sending, well, then, of course, it's just going to wait. So hopefully that makes sense, right, why they've got to send at different, different random times. Right, modern Ethernet, well, uses switch instead of hubs. Right, switches to our MAC IP address table of devices on the network. Right, therefore they can send the packets or frames, right, to the correct devices. Right, switches, well, yeah, okay, so I think we mentioned this many times, right, support unicast, multicast, broadcast, right, also support full-duplex. Right, switches also can have a buffer which can temporarily store packets when under high load. Alright, so if we go on to the next part, well, the World Wide Web versus the Internet. So the World Wide Web, that's a collection of web pages linked together and accessed via the HTTPS protocol, again, hypertext transfer protocol, right, S meaning secure. Right, Internet, well, that's going to be internetwork, so the worldwide connection of devices and infrastructure. So infrastructure being cabling, satellites, routers, etc. Right, it's going to communicate, or I guess route data, route packets via IP. And any digital data can be sent. So web pages, media, right? So images, videos, right? Emails, files, programs, text, right? Etc. So effectively, the internet is a superset containing the World Wide Web. And if we see that, so I guess the blue one is going to be the internet. And then if we say, the World Wide Web, so the World Wide Web is basically just all of the websites, right? All of the web pages. The internet, that's also going to include. And to be honest, when we say clients and servers, I mean that's quite vague. I guess clients, okay. So when we say clients and servers, I mean basically just end devices, right, like physical devices. The internet is going to use different protocols, for example, IP, TCP, UDP. Right, it's going to be infrastructure, cables. I guess it's also going to include emails, files, right? SSH, telnet, right? Let's say video streaming. I guess sort of music streaming. Right, so as mentioned, the internet can be considered a huge WAN, right, wide area network. It was never designed as a whole, it simply grew naturally with millions of people adding servers and I guess even more acting as clients, right, just people, browsing, sending emails, right, watching videos, right, etc. Right then, ISP, Internet Service Provider. So since the internet wasn't officially designed, however, I guess it has developed into a hierarchical model. So there's going to be three types of ISPs, right? One will access or tier 3 ISPs. That's going to allow an individual business to connect to a regional ISP. So access ISPs, I mean, they could literally be just in your city. This can be quite small. Right then, regional, okay. So regional or tier 2 ISPs, they're going to connect the local access ISPs and provide national or regional coverage. Right then, global or tier 1 ISPs, they're going to provide the global backbone, for example, the undersea fibre optic cables, the satellites, etc. So as you can probably imagine, obviously, okay, so there's going to be a lot of, for example, access ISPs, right? Whereas in contrast, there's going to be relatively, so there's going to be, relatively few, right, global or tier 1 ISPs, since, the price is, so much more expensive for having, undersea cables and satellites. However, let's say many ISPs will fall into multiple categories. So, for example, China Mobile, or AT&T, so in America, BT in the UK, right, they're going to be all three. So they're going to provide, local access in your city. But they're also going to provide, let's say, the undersea cables, right, the satellites that are sort of used by everyone. Alright, so I guess let's say our packet might be routed then from someone on one ISP to someone on another ISP. Don't get confused about stage 1 to 3. This is different from tier 1 to 3, as we mentioned earlier. So, right, stage 1, point of presence. So packets are sent to your ISP's local router in your city or your region. Right, then I guess you're going to have to connect those points of presence. So I guess here we just see the different cities, and right, packets can be routed via their own ISPs while cabling or shared cables, right, to a different city. Or okay. So so do it. So a different city, right, or different point of presence, right, if possible. Right, if not, then we need stage 3. So if we're actually talking about using different ISPs, then you're going to need an internet exchange point. And an internet exchange point, that's basically where the so that's where the packets on, let's say, one cable, right, can switch over, let's say to so that's where the packets on one network or one cable can switch over, right, to the different cable, the different ISP's cable. So let's say here, if someone on this purple network is sending, let's say, to this orange one here, then of course it's going to be sent right to this IXP. So the XP in exchange, right? Then of course, then it's going to get switched over onto this. Where are we? Okay, here we go. So it's so it's going to get switched from this purple line right onto this orange line, or this orange cable. Then of course, that's then going to get sent, right, and just arrive at this final destination. Or and I guess well, just to see an example then, well, tier 1, the global backbone. So this actually only shows the undersea cables. This doesn't actually show the on-land cables. And of course, yeah, there's also going to be many cables, sort of underground, right? Yeah, sort of on the land. And if we actually just sort of zoom in on one specific cable, well, here, for example, I guess you can see the sort of different places it goes to. You can also see the different owners. And again, these are going to be the tier 1 ISPs, right? China Mobile, China Telecom, right, etc. Yeah, sort of various others there. Right, so if anyone's actually curious, well, this is the website, right, submarine cable map, and I think it's quite interesting. Yeah, just go to your country, your region, right, yeah, see, who owns the cables, etc. Right, then if we talk about buffers, so the buffer is going to store data until the router is available to process it. So if the data coming in is too fast, then we can, okay. So let's say if the data coming in is faster than we can process it, well, then we're going to need a buffer, to temporarily store that. Alright, so I think, yeah, we mentioned this about routers, so our home office, right, okay, so also our, so our access regional global, right, so our tier 1 to 3, 3 to 1 ISPs, right, also anytime a cable splits, because if a cable splits, well, then we need to know, do we send it down this cable, or do we send the packets down, the other cable. Right, and I guess if you just want to sort of trace that, well, you can use traceroute. So here I'm just using traceroute, where I go into Bing. And if you look, well, this here, right, 192.168.0.1, well, that's going to be a private IP. So that's actually just, well, okay. So I guess that's probably going to be my device, or just, well, the router. Then I guess, well, finally, then we're going to get to, right, Bing's IP at the end. So then if we talk about circuit switching, right, that's going to use, well, the PSTN, right, the public switch telephone network. So calls will be sent along a telephone line to an exchange. Now, if we look at the exchange, well, basically, if we see in the sort of top picture here, we're just going to have all of these different ports, all of these different wires. So let's say that if we have someone in, well, let's say Manchester, and they want to call someone in Melbourne, well, let's say this one, this is probably going to be, let's say, the Manchester office, or yeah, the Manchester exchange point. You're then going to have the person who's, sort of physically unplugging, sort of plugging it in. And let's say then maybe they want to go, let's say, from the Manchester exchange, right, to the London exchange. So let's say if this is like the London, sort of the London port, well, what they're going to do, they're going to sort of unplug this wire, and of course, yeah, just sort of, connect it into the London port, right? Then I don't know, from London, right, maybe it then goes to Paris, right? Then it goes to wherever. Obviously, eventually, it's probably going to end up in Sydney, right? Then of course, yeah, they can then plug that into the Melbourne. Alright, so hopefully that makes sense how it works. Now, again, traditionally, you'd actually have a person doing that. I think these days this is actually done digitally. But the actual concept is the same, where you're actually going to need a physical wire, right, from, well, the sender to the receiver. And that connection has to be established before any communication can take place. Right, so if we think why this was used, when the internet was first getting popular, let's say in, well, the 90s, I guess, well, even, early 2000s, we didn't have the millions of kilometers of fibre optic cable, right, like we have today. So instead, well, since we had the existing telephone line infrastructure, well, then data was just sent along that. And yeah, that had existed, well, for the past 100 years. However, there was a problem. Well, telephone lines are going to transmit data analog. Okay. So let's say telephone lines are going to transmit analog signals, right? While the internet is going to operate digitally. Therefore, we need a modem, and that modem, well, that's going to convert from analog to digital, and vice versa. Just so they could, understand each other. Right, and yeah, this we kind of mentioned, right, packet switching, circuit switching. So there's two ways we can transmit data from a source to a destination. Right, I guess, well, now let's compare them in more detail. So packet switching, well, that's what routers used. Right, circuit switching, well, that's what, PSTN used, for example. Right, public switch telephone network. Right, so features of packet switching. So data is sent without a connection being established. So this we can say is a connectionless, connectionless, transmission method. Right, between the sender and receiver. This means that establishing the connection is fast. But the receiver may be unreachable. For example, the device is turned off, right, there's a network error. So what this is saying is, well, basically we're just going to start sending the data. And if they receive it, well, then I guess it's good, right? If they don't receive it, well, then I guess there's not really much we can do. But we don't need to check that they're available beforehand. So since we don't need to check if they're available, well, then it's going to have a lower initial latency. Since we're just, kind of immediately sending. Right, routers going to forward packets onto the next hop, again, based on their routing table. Data, let's say an image, will be split into many smaller packets, let's say not larger than, 1460 bytes. right, packets may travel different routes or arrive out of order, right, then they'll have to be reordered at the destination. Now actually this reordering is going to happen if we're using TCP, right, the transmission control protocol. Now TCP is basically going to be reliable because, well, one, it's going to sort of reorder the packets if they're in the wrong order, right? Also, if any packets don't arrive, well, then it's going to request that they're resent. Whereas if, for example, we look at UDP, now UDP is a different protocol. Now UDP is not going to have any of those checks. So if the data arrives out of order, well, then it doesn't matter. Again, if some of the data doesn't arrive, again, it doesn't matter, right? Okay. So it's not going to ask for it to be resent. Now you might think, well, why would you ever want that? But let's say, for example, if you've got a video stream, now if, let's say, you have some video that, doesn't quite arrive, well, you're not going to be able to, sort of go back and sort of ask for that part of the video to be resent. Because the thing is, well, by the time you get that, well, that part of video, happened 1 second ago. And I guess you've already got, sort of like newer parts of the video already. So if you're talking about, for example, right, okay. So let's say you're talking about, okay. So let's say you're talking about like a live phone call, or like a live stream, live video. Then that's why you're going to have to use UDP, because you don't have time to go back and sort of request the data again, since that data has already happened in the past. Right. So let's look at the advantages then. Packet switching. Well, it doesn't require the dedicated infrastructure for each user. Right, many people can, I guess, share the same infrastructure, right, the same fibre optic cables, right, therefore it's going to be cheaper and, I guess, more scalable, because let's say if you've got, the modern internet, billions of people using it, well, you're not really going to have, sort of PSTN where you have sort of, billions of individual, one-to-one connections. That's just not going to be scalable, on a sort of a global scale. Right, because of this, well, there's better utilisation of hardware, sort of shared hardware. Right, here I've put in orange where it can be faster, because while packets can be sent along the fastest route, I guess also packets can be sent sort of simultaneously along multiple routes. So you can get kind of like a simultaneous, sort of simultaneously sort of receiving the packets. Right, well, no connection required, right, connectionless, right, therefore, well, lower initial delay, right, lower initial latency. Alright, and this one, so reliability can be built on top, right? Okay. So as mentioned, a higher level protocol like TCP, right, that's then going to resend packets that don't arrive and reorder them, right, upon arrival. Whereas again, UDP is not going to do that. Right, disadvantages, packet loss. Some packets might not arrive at the destination because, let's say a misconfigured network, a broken router, broken cabling. I guess full buffers. So if the router's buffer is full, well, then it's not going to be able to receive that incoming, those incoming packets. Right, also packets can arrive in the wrong order. Right, variable latency, because packets traveling different routes, right, are going to take different times. So I guess you might have to wait, if there's a particularly slow route. I guess also header overhead, so you also require a small amount of extra data needed in the packets. For example, the header, right, the source and destination IP address, the packet length, right, the version. So whether you're using IP version 6, IP version 4. Right, there's going to be a checksum, basically checking that the data is not being corrupted. Right, time to live. So if you get a situation where the packets are being sent, round and round in a circle, basically a kind of infinite loop, well, the time to live is basically going to solve that. Where each time, okay. So each time the packet is kind of, let's say read or intercepted by a router, well, the router is just going to decrement this time to live value. And if the time to live value gets to 0, well, then it's just going to, drop the packet. Because if it gets to 0, well, then it can assume that there must be some error. And, the packet is just getting, sort of, sent round and round, right, in a circle, so in a circle, or, so in a loop. I guess where some of these issues can be handled, for example, rerouting and, again, higher level packets. Higher level protocols like TCP. Right, again, that's going to sort of help solve some of these issues. Right, then if we look at circuit switching, so this is what the phone connection used to use. Right, so a physical link between the sender and receiver is required. This could be with someone on the other side of the world. So you could literally have like a physical line, 10,000 kilometers, right, connecting the two people. Right, so the connection must be established before the communication can begin. So on the one hand, that's reliable because I guess you can kind of make sure they're available. Although, of course, that does have the higher initial latency, right, since you have to check. Right, channel is dedicated for only those two users for the duration of communication. And in some ways that's good because, one, it's going to be fast, it's going to be reliable. However, at the same time, it's also going to be expensive because if you think, well, you're basically having to rent that entire line, for that entire time. So if you're having a phone call, let's say for like 1 hour, well, you're effectively having to rent that entire line for 1 hour. And that's also why, basically, before, the longer the distance of the phone call, well, the more expensive it would be, because in effect you're having to rent more wire. If, for example, you'll say, okay, so let's say this is, I don't know, like city A, right, city B, city C. Now, if you're calling, obviously, well, city A to city B, well, of course, you're not having to rent that much wire. But let's say here, well, this is going to be like F or something, right? If you're calling, well, from city A to city F, well, then, of course, okay. So then, of course, you're having to rent a lot more wire. So I think hopefully that makes sense. Right, lease lines. So we did actually mention this when talking about WANs, right? Because a dedicated connection was required, then if no connection was available, well, someone wouldn't be able to connect. So let's say you're a company that always requires a dedicated connection. Well, then you can actually rent a permanent line, right, i.e. a lease line. Although, of course, that's going to be extremely expensive. Right, so again, let's look at advantages, disadvantages. One is going to be reliable. We can ensure the receiver is reachable before sending. Right, dedicated channel required. So on the one hand, well, it's reliable, but also high bandwidth. Right, however, it's also a disadvantage because, well, one, it's going to be wasteful, it's expensive. And the reason we say wasteful, well, let's imagine you've got a, I don't know, something like, well, okay. So even probably on those old phone lines, let's imagine those old phone lines can support, like, I don't know, 10 megabits per second. Well, if you're having a phone call that only uses, like, say, 50 kilobits per second, well, then you're basically wasting all of that bandwidth, right, since no one else can use that wire. Right, however, it is going to be suitable, well, for long communication, right, e.g. phone calls, well, again, because it's reliable. Although if you think, well, it's also expensive, so in sort of practicality, right, maybe it's not that suitable for phone calls, because, yeah, you probably don't want to be paying, huge fees every time you're calling someone. Right, another advantage, well, data will arrive in the correct order. And if you think about that, well, that's because you're sending, sort of, well, one, okay. So basically, because you're sending the data in a continuous stream, and it's not getting sort of split up into packets and sent along different routes, right, like it is in packet switching. Right, system also has backup generators, and I think the reason for this, well, since it was developed older, right, since it was also required for, let's say, an emergency. So I guess if there's a flood, right, if there's a fire, if, I don't know, some criminal, right, then because you always need to call, well, let's say, like 999, 911, whatever the sort of, emergency service line is. Well, since you always need to, call the emergency services, well, that's why this system was built with many backup generators. Whereas I guess, let's say, packet switching, probably things like, routers, they're not really going to have a backup generator, built into them. Right, disadvantages, well, as mentioned, right, if all the channels are being used, then you won't be able to connect, So I guess you could have a leased line, but again, right, extremely expensive. And even here, just for regular use as well, it's also higher cost, right, because of this, well, dedicated channel requirement. And in orange, well, higher initial latency. And the reason I put this in orange is because in reality, I mean, probably that initial connection, it's probably not going to take that long. Although if it was, okay. So if you're talking about the old days where you had someone, physically unplugging and plugging them in, well, of course, so that's going to be an extremely high latency. But these days, when it's done digitally, this initial latency is probably still less than 1 second. Alright, so then if we talk about cloud computing, so cloud computing, well, the definition is the provisioning of computing services via the internet. So I guess what kind of renting, right, provisioning. Right, clouds can be either private or within the company or public, right? For example, AWS or Amazon Web Services, Baidu, I guess Azure, right? Microsoft Azure, Alibaba, Tencent, right? Google, etc. Right, so just some pictures. People are probably familiar with some of these. Alright, so it seems the animation is messed up. Alright, so let's say for the private cloud option, well, there could be three choices, right? One, the organization can create and manage their own on-site cloud. So I guess this is kind of the most private. Right, the organization can then outsource to a third party to create and manage their on-site cloud. And the reason for that, well, maybe the organization doesn't have the staff or expertise, right, to create and manage the cloud themselves. Right, therefore they can pay a sort of specialist company, to come in and manage it for them. Right, okay, or the organization can outsource to a third party to create and manage an off-site cloud. So even though this is off-site, well, it's still going to be private, right, since this cloud is only for this one company. And I guess we've said, right, so 1 is going to be the most private, right, 3 is kind of the least private, even though, Again, okay, these are all still considered to be private clouds. Alright, so in contrast, well, then there's going to be the public cloud. Right, so here then the user company only has one choice, and that's to use the cloud provider's public infrastructure. So in this situation, well, customization is more limited, right? Yeah, not possible or expensive. Because if you, for example, phone up Google and say, yeah, I want you to install, some custom hardware, well, realistically, like, they're not going to be able to do that. If you're some massive company that's having, sort of, well, like, okay. So if you're some massive company that's going to be spending, millions upon millions with them, well, then they're probably going to be able to do it. But yeah, just for regular users, right? Yeah, that's not really going to be possible. All right, so yeah, let's talk about the different services that can be offered. Well, so one, what infrastructure provision. Also what IaaS, right? So infrastructure as a service. This is renting hardware directly. So maybe you want to do some graphics processing or some AI model, training. Well, then, for example, you can rent a load of GPUs, because probably you're not going to be able to afford let's say 100 NVIDIA GPUs. But if you just want to rent them for, I don't know, let's say like a sort of a couple of hours while you're training this model, maybe that's going to be more affordable. Right, so platform provision. Let's say renting different operating system, different environments. I guess sort of different setups, right, configurations. Right, software provision. Let's say Google Docs. Something like Baidu NetDisk. So Baidu NetDisk, basically the same as Google Drive, right, just cloud storage. Of course, OneDrive again, right, just cloud storage, right, Microsoft. Right, and these are also more commonly IaaS, P and S. So okay. So obviously I, right, infrastructure as a service, right, platform as a service, right, software as a service. Right, so the advantages of the cloud, well, one, you get remote access. So let's say if you have a company, well, then your employees can access those files from anywhere. Even if they're in, different, different country. Maybe they're on the train. Right, collaboration. So employees can work on the same files simultaneously, because I guess you have one copy of the files on the cloud, and then of course they can all collaborate, right, by accessing that same file. Of course, okay. So in reality, when I say one copy, of course you're also going to have a backup as well. But I guess one sort of main or active copy. Right, can also be used okay. So talking about backup, cloud can also be used as backup. Although I guess this is quite expensive. The thing with saying remote backup, this is good, because actually if we think, I think it's maybe chapter 8, which talks about backups. Now, we don't want to have all of our backups in the same sort of place, because, let's think for the moment, let's say, Los Angeles, right, they've had the wildfires. Now, let's say if you had, your servers in like Los Angeles, and all of your backup data was all in Los Angeles, potentially all of that is going to get destroyed. Whereas if you have things in, different cities, different countries, then of course it's less likely to get, all sort of taken out by natural disasters, or all affected by, let's say, the company closing, or I know some political situation, right? Some like war, for example. So big cloud company, Microsoft have better security than the system we can make ourselves. So this is saying, if you rent from, I don't know, AWS or Google Cloud, maybe they have better security, than the solution we can make ourselves. Right, here I put this in quotations. So some people say it's going to reduce complexity, right, if it's a public cloud, because I guess, someone else is going to handle, the managing of these servers. Although for me, I would actually say that the cloud in many ways can actually be sort of more complex. Okay. So if people are actually familiar with clouds, like if you sort of go into their websites, it's just like hundreds of different options, right, hundreds of different projects. And I think the other thing is that actually, if you do something yourself, then there's actually kind of a lot of resources online, right, which you can learn from, especially with ChatGPT. Now, if you're using a cloud, then there's kind of less documentation, because basically the only documentation you have is, from, within that cloud. All right, and so I guess, disadvantages, one, you're storing data with another company, right, therefore you have to trust them. This could be, security issues, right, sort of privacy issues. And I think actually for some situations, let's say you're storing like financial records, medical records, then there's going to be quite strict kind of legal requirements that you have to let's say abide by, and maybe storing something in a public cloud is not going to meet those kind of legal requirements. So here I say it's going to be much more expensive than traditional servers, because let's say if you sort of buy a traditional server, you're going to have the sort of one-time cost of purchasing it, or just sort of renting it if it's like a VPS. Whereas the thing is with a cloud, a cloud, you're basically paying for the sort of scalability. where let's say you have a website, and if your website becomes popular, well, then it's going to automatically, allocate more servers to it. So on the one hand, while that is convenient, but for that convenience, I mean, you can actually be paying, let's say, 100 or even 1,000 times more, right, than if you just kind of, rented servers directly. Or also some software can be run effectively, right, when distributed across multiple servers, right, e.g. databases, because if you think, well, you can't just have one copy of the database, you're probably going to want to copy, okay. So you're probably going to have backups to that database. You might also have some query which needs, kind of data from, right, multiple different shards of the database, right, in different locations. So in that case, right, that's going to be slower. Also, less customizable and less control, right, compared to having your own servers. Because if you have your own servers, well, basically you can do whatever you want. Obviously, cloud, well, probably the cloud company is going to, lock down certain features, right? They're also going to have, terms and conditions. So if you're using it, I don't know, let's say to mine cryptocurrency, well, that's going to be, against their terms and conditions. Obviously, if you're doing anything illegal, that's what kind of goes without saying, right? That's generally going to be against their terms and conditions, unless it's some, sort of dodgy pirate cloud company. Alright then, bit streaming. So okay. So basically, bit streaming is going to be like a constant flow of data. Let's say a live video phone call, right, watching a movie, right, listening to music. So unlike a regular download, then a stream is of unknown, possibly indefinite length. And I guess, that's true for real-time streaming. That's actually not true for on-demand streaming, because I guess on-demand streaming, there the media has been pre-recorded. So in that case, we do actually know the file size of it. And I guess, just an example of a, river, right, stream of water. Alright, so on-demand, on-demand streaming, right, the streaming exists from a source that already exists. So if we look, let's say, for example, on Netflix, I guess Disney Plus, so if the thing has already been recorded, then it's going to be on demand. Right, real time, here's a stream coming from a live source, so let's say, like a live radio station. I guess, live sports, right, that's going to be an obvious one. I guess, various websites like, let's say, Twitch, some, or like gaming streams, right, whatever. Alright, so some examples, I guess, on demand, right, YouTube, SoundCloud, Netflix, right, real time, live sports, right, Twitch, radio, as mentioned. Alright, so hopefully these should be fairly obvious which. If we look at the first one, so the first one we see, actually this one is live, because here it says live. This one, of course, pre-recorded, and we can actually see the time in advance. Obviously, Breaking Bad, that's going to be on demand, right, since, that's, pre-recorded. Right, a Zoom call, that's going to be real time, right, it's happening live. I guess, football, if the football is live, of course, that's going to be real time, right, same for the flight tracking. If you think, QQ Music, that's basically the same as iTunes, or, I guess, like Spotify. Right, so these, and also, torrenting, right, peer-to-peer. Since the files, or I guess, the music already exists, right, that's going to be on demand. Alright, so just to recap, on demand, right, media files are stored on the server and converted to a streaming format, right? Therefore, we can pause, rewind, fast forward, right, because this has already been pre-recorded. Right, often it's going to be better quality because we can make use of buffering. So if, let's say, the connection sort of temporarily drops, or, temporarily sort of decreases in bandwidth, then I guess that's not so much of an issue, because hopefully we've kind of pre-buffered, the next 30%, okay, so not 30%, okay, hopefully we've pre-buffered the sort of next, 30 seconds of, video or, audio, in advance. Right, then we'll look real time, so again, events capture in real time, and the live media are sent. Now, because it's live, therefore we, right, okay, so actually, this is kind of a bit different, because, some servers will also save this. Although I think in the exam, I guess we're just talking about the simple examples. So if we assume that, this real-time stream is not saved anywhere, then once it's been sent out, okay, so once this has been sent out, then effectively, that live stream is just gone. Right, therefore we can't rewatch it, we can't pause it. Obviously we can't fast forward it, because, fast forwarding means, going into the future. Right, I guess packet loss over UDP can also be an issue, so parts of the video and audio will be lost. Right, therefore we're going to get jumping audio, or sort of some corruption. Alright, and I guess that's just saying a sort of alternate situation. Right, then if we look at bit streaming, so the media player, the media player is going to request data from a media server and stores it in the buffer. Right, the media player plays video as it arrives in the buffer. If the buffer reaches the high watermark level, so this is kind of like the full level. So if the buffer is nearly full, well, then the media player tells the server to stop sending. However, if the buffer hits the low watermark level, so effectively like nearly empty, well, then the media player tells the server to resume sending. And I think people are familiar, let's say with YouTube. Now, when you're watching a YouTube video, right, if you actually look at the kind of like buffer, sort of video level, like you'll often have it where if it gets to the point where the video has nearly reached up to the sort of buffer point, well, then we're going to get okay. So then we're going to get it where I guess what the sort of website is going to send a message to the server, right, and then it's going to sort of download the next 30 seconds of video, or stream the next 30 seconds of video. Right then, when that 30 seconds is almost played, right, then it's going to stream, the next 30 seconds. So that's why it kind of happens in like rather than a constant flow, we get almost kind of like I guess kind of like batches. So we're going to get like a batch where it's going to download, and then a batch then it's going to sort of stream the next amount. Alright, so actually this diagram is slightly wrong because I guess if we're talking about the data flow coming in this way, so we say well the buffer is going to fill up this way, right? Therefore this one should actually be the high watermark. When it's sort of nearly empty. Whereas sorry. So this one should be the low watermark rate when it's nearly empty. Okay. So this one here at the end, well, this should be the high watermark. Of course, okay. So when it's nearly full. Right, then let's look again. Right, advantages, disadvantages. So well, one, we can play immediately without having to wait for the whole file to download. So if you're downloading some video. Let's say like a movie, well, of course, potentially that can take a long time, whereas while streaming, we can just immediately play it. We also don't need to store large files on our own device because, well, once we've streamed it, it's just kind of like, lost. Basically, it's just going to be stored temporarily in RAM. It should never actually be saved to secondary storage. Right, I guess it's also harder to pirate because let's say if we're, watching, some football match, well, it's going to be difficult to actually kind of save that, right, permanently. Okay. So let's say it's going to be more difficult to save that permanently. I think there are solutions to do it, but I guess it's okay. So it's still not as easy as just downloading a regular file. Right, disadvantages, well, it is going to require an internet connection, so we can't sort of pre-download things in advance and sort of save them. Right, I guess we can also get buffering as an issue, right, lag on a slow connection, or alternatively a high resolution video. Right, so it's going to use lots of bandwidth, right? Especially, let's say streaming, let's say the same song hundreds of times. So in that regard, it's actually better to download it once, right, rather than streaming it 100 times. Right, okay, so then if we look at IP addresses, right, IP is going to stand for Internet Protocol. Right, when first built, a public IP address would uniquely identify every device in the world. So effectively, it's like a house address, but uniquely identifying a device on a network. And actually, maybe a house address is not the sort of best analogy because actually, what we'll see in a minute. Well, let's say you have a computer. Well, you're going to have multiple processes running on that computer. So let's say you have like a web browser like Chrome. Now, probably you're going to have multiple tabs open. Now, if you just send to this IP address, well, then the operating system is not going to know, is it for tab 1 in Chrome? Is it for tab 2? Is it for tab 3? Is it for, I don't know, like some other like game that you're playing? Right, is it for, I don't know, some, sort of streaming thing you're watching? So actually what you're also going to need, well, not only will you need the IP address, okay, you're also going to need the port number. Alright, so IP version 4, well, this was planned in the 1970s and introduced in 1982, right, initially, well, just military universities, they didn't believe it would grow to the size it did. Right, so if we think how many bits are in IP version 4, well, there's going to be 32 bits, right? They're written as 4 groups, right, in the numbers, well, 0 to 255 denary. Right, for example, 192.168.0.1, and that's going to be a private IP. And if we see in a minute, well, private IP, there's going to be, I think, 3 different private IP ranges. One is 192.168. I think one is 10. I think one is maybe 172 or something like that. Right, anyway, okay, that's going to give us, 2 to the power 32 different addresses, effectively, 4.3 billion. However, I guess, as we'll see, 4.3 billion is not enough. Well, one, we've got about 8 billion people in the world, right? Also, like, many people have more than one device. Lots of people have, let's say, okay, so lots of people have, let's say a laptop, a desktop, right? Maybe a phone, right? Games console, car, obviously, like, CCTV cameras, right? So all of these things are going to need IP addresses. Right, I guess, in 1982, you can actually see kind of how many people had, okay. So I guess here we can see how many people were using, the internet, right, ARPANET. in 1982. Obviously, well, 1969, right, just, yeah, even smaller there. Alright, so I think we mentioned this, yeah, 8 billion people, right, people have multiple devices, right, basically there's not enough IP version 4 addresses. Yeah, so the number of IP addresses is not going to be able to uniquely identify all devices in the world. Right, therefore there had to be changes, for example, subnetting dynamic and private IP. Yeah, and actually, I guess we're also IP version 6, although, yeah, IP version 6 did come later, right, compared to these other three. Right, so let's say the format, well, there's going to be the network ID and device ID. Let's say, for example, a company could have the network ID, well, 200, 200, 200, right, so that's using 24 out of the 32 bits. Right, that then gives them 8 bits remaining for the device ID. So valid IDs for the device would hence be, well, 200, 200, right, okay, dot 0, right, so, well, 200, 200, 200, right, dot 255. Because if we think, well, each group can go, right, from 0 to 255. Yeah, right, hence, well, with 8 bits for the device ID, or, well, the host ID, right, they would have 256 different, well, host or, yeah, sort of device IDs available, or, yeah, IPs available. Alright, so I guess the split can actually be any values that add to 32. So here I just choose, well, 24 bits for simplicity. Although we could have, I don't know, let's say 17 bits for the network ID, right, and 15 bits for, well, the host ID, the device ID. Alright, so let's just look at some examples. If you want, pause the video, right, and let's think, what are these valid or invalid? So the first one, hopefully we can see what invalid, because what the first group, what 1234, well, that's bigger than 255. Right, the next one seems valid, right, we've got, well, 4 groups, right, all are 0 to 255, yeah, they're all separated by the dot. Right, then if we look at the next one, so again, 256, yeah, that's too big. Right, then if we look at the last one, so count how many groups, here there's actually 5 groups, yeah, therefore, right, that's invalid. Right, then if we look at how we actually separate the network ID from the device ID, right, so traditionally, well, there's been 3 ways to achieve this. Right, one is IP classes, right, this is not really used anymore. Right, then, well, CIDR, right, classless interdomain routing. Right, then, well, finally subnetting, and subnetting is the one that we use today. So if we look at the first one, well, IPv4 classes, right, so here we see this quote, right, basically they've been, well, deprecated since 1993, right, not used since 1993. Although I think the reason that they might still ask this in the exam, because if we look, well, this is in the book, yeah, technically it's in the syllabus. I think the reason they want you to know this is because, well, basically we have to see the problem of IPv4 classes, right, in order to know why they then developed, well, obviously, yeah, subnetting and, well, CIDR. Yeah, okay. So I guess, well, CIDR came first, right, then subnetting, right, came after. So let's say class A, well, class A is going to use, right, the class identifier 0, right, okay, then we're going to have 7 bits for the network ID, right, 24 bits for the host ID. And if we look at this, right, these are all going to add up to 32, because if we think, right, okay, so if the class identifier is 0, well, that's going to be 1 bit, right, and then, well, so 1 bit, right, plus 7, right, plus 24, well, that's going to be 32. Right, here if we look at this one, and yeah, where's the pen? Here we go. So class B, well, 10, that's going to use 2 bits. So, well, 2, right, plus 14, yeah, plus 16, well, that's going to be 32. Right, likewise, class C, well, 3 bits, right, plus 21, plus 8. Again, that's also going to be 32. So, for example, let's say we have this IP address. Well, since this starts, right, 110, right, therefore we know that's a class 3. Right, therefore we know, well, these 21 bits must represent the network. I guess what these remaining 8 bits, right, they must represent the host. Yeah, all right, and then if we look at the number of different network IDs, device IDs, like basically the way we do that, let's say here then, if we look at class A, well, since there's 7 bits for the network ID, well, then what that means is going to be, what, 2 to the power 7, right, that's equal to, okay, that's equal to 128 different networks. Now, basically, there's going to be a problem with this, because what this means, well, only, okay, so there's only going to be 128, like, different, well, companies, right, governments, militaries, that can have Class A in the entire world. And obviously, that's not going to be enough, because, well, there's going to be lots of people that are going to want to have Class A network. Likewise, if we think of Class B, well, Class B, again, right, there's only, well, 16,000. And if you think, well, a lot of, let's say, small businesses are going to want this, because let's say if we have, I don't know, like 256 different, okay. So let's say we have 257 different devices. Well, 257 is going to be bigger than Class C, right? Therefore, okay. So therefore, in that case, well, we're probably going to want a Class B. Like we can actually get it where we have, well, 2 Class C networks, you know, combine them together. But yeah, that's going to be a little bit difficult in terms of configuration. Yeah, we're probably going to need a bridge or something, right, just to connect those networks. Yeah, so that's kind of a problem. And even if we look at Class C, well, here we only have, what, 2 million. Now, effectively, what that's saying is, well, we can only have like 2 million, different homes, right? 2 million different homes with a router. Now, of course, in the world, well, yeah, that's obviously, well, nowhere near enough. Yeah, so okay, so again, if you want, you can pause that, have a read, although, yeah, let's just skip. Right, so I think this one we mentioned, right, so suppose a company has 150 computers, right, but they want to be on 7 different LANs, because, well, maybe these LANs are in different buildings, right, different departments. Right, what they would need to do, well, okay, so they would need to buy 7 Class C networks, right, that would mean, well, that would give them, 1,792, or yeah, 1,792 different addresses. Right, but since they only have, 150, computers, devices, right, that means, 1,642 of these addresses are wasted. Yeah, so hopefully that makes sense. Right, so in order to kind of solve this problem slightly, and I guess, right, okay, really, so to solve the inflexible split, right, i.e. only 3 classes, okay, so, okay, let's say to solve the inflexible split of the network ID and host ID, right, portion of the IP address, that's why CIDR, well, classes inter-domain routing, was developed. Right, this is going to add an 8-bit suffix to the IP, so yeah, here we can see that here, right, just these extra 8 bits. Right, the suffix is going to specify how many bits are for the network ID. Right, the remaining bits of the 32-bit right, IP version 4 address would therefore be the host ID. So let's see in this case, alright, so actually I guess here it's telling us, so here we're saying 21. So what that means when we say /21, well, therefore it means what the first 21 bits, here we go. Right, the first 21 bits are therefore going to represent the network ID. Right, therefore, what the last 11 bits, okay. So the reason it's going to be 11 is because, well, everything, right, 32 bits total. Obviously, 21, 21 used for the net ID. Right, therefore, well, 32 minus 21, right, 11 remaining. 11 therefore for the host ID. Yeah, I guess that's kind of what that says. Right, also CIDR, this also doesn't waste 1 to 3 bits for specifying the class. Since I guess we can kind of just eliminate that, right, by having this suffix instead. Right, also CIDR, so these IP addresses are also compatible with the original class-based IP system, simply by setting the suffix to 8, 16, or 24 respectively. So if we think about the way that works, right, let's say if we set it to 8, then okay, so what that's saying then is because, well, this one here is going to use 8. Let's say, for example, this, well, if we have 0, so of course, right, okay, so of course, okay, so this is going to be 1 bit, right, this is going to be 7 bits, right, therefore in total that's using 8. If we look at this, well, this is going to be 2 bits, right, this is 14 bits, right, therefore in total that's 16. Obviously, so this one here, well, that's 3 bits, right, so 3 plus 21, right, that's 24. Right, that's why if we use these suffixes, well, these can then be used, to kind of represent or be compatible, right, with this original class-based IP system. All right, so I think that's just what that says there as well. Right, then finally, well, there's going to be subnetting. So another approach, and this is the one currently used today, right, this is subnetting, and if you want to see your subnet, well, for example, on Windows, right, run ipconfig, right, well, space, right, then /all, right, you're going to notice the subnet mask for the network. And here I guess we can see that, right, 255.255.255.0. So, okay, so let's see how this works, right, then we can explain it. So again, well, IP version 4 address, right, split into network ID, host ID, right, subnet mask is used to determine if a bit corresponds to the network or host ID. So if the subnet mask has a 1, well, then it means it's the network, right, if there's a 0, well, then it means this bit corresponds to the host. So let's see here, well, 255.255, right, .0. So if we say this one, so here then we see 3 255s, right, therefore what the first 24 bits are going to be for the network ID. Then finally what we've got are 8 ones, because so if we look at this, right, this, okay, so this last group of zeros, well, therefore there's going to be 8 bits for the host ID, or 8 bits for the device ID. So let's say an IP address, something like this, well, if we're using this subnet mask, well, then what it means is what the first 24 bits are going to be the network, obviously, and then, 55, right, that's going to be the device on that network. Alright, so common subnet mask, well, 255.255.255, right, .0, and then, 255.255, right, 00. I guess, right, the first is more common worldwide, and if we think about that, that's because, well, this is going to give us, 256 different devices. And because of this, well, there's actually going to be well 2 to the power of 24 like different kind of networks, you know, that can use this. So basically the reason that's common is because, well, if you just have like a home network, well, if you have a home network, right, 2 to the power 8, right, 256 devices, I mean, this is going to be more than enough. Now, this one here, this one is going to use 16 bits. So 16, is it, 65, maybe 535 or 536? Yeah, I think something like that. So if we have that, well, then we're not really going to need that many devices, you know, on a home network, for example. Okay. So so that's why this subnet mask is, you know, probably the most common. All right, I think, yeah, that's what we sort of said. Right, so going back to our sort of old example, well, let's imagine we have a company, again, we have, what, I know, 150 devices, right? We want to sort of break them into different networks. So subnetting, well, that's breaking a big network into, well, multiple smaller subnets. And again, let's imagine we have like different departments, right? Maybe a finance department, right? Research development, customer service department, right, etc. Now, maybe we don't want the research department to have access, let's say, to the financial records, right? Likewise, we don't want, say, the financial people to have access to, you know, sort of customer details, right? Therefore, we might, okay. So therefore, we want to keep them, right, on separate networks. The other advantage of, let's say, if there's a hacker, well, if the hacker manages to hack, let's say, I know, the sort of customer service record, well, right, okay, not the customer service record, the customer service network. So if a hacker hacks the customer service network, well, then if we have good security, right, good network separation, they shouldn't be able to go from that network onto, let's say, the financial network, or yeah, onto, you know, the research network. So that's going to be another advantage of subnetting. Right, so how this works, well, let's assume we have, you know, 8 bits remaining for the host ID. Well, then we can split this even further. So we can say, well, we're going to use 3 of those remaining 8 bits to represent the subnet. And, well, then obviously they have the 5 bits remaining, right, to represent, well, the host ID, right, the device ID. So that would then give us 8 networks with, well, 32 devices on each. And the reason we know that is because, well, here we're using 3 bits. Right, so 2 to the power of 3 is 8, right? The remaining 5 bits, well, 2 to the power of 5, yeah, that must be 32. So that's going to give us, what, 8 networks with 32 devices, okay, rather than one big LAN, or yeah, one big network, right, with 256 devices. Alright, so I guess here you can just see that again. Pause the video if you want to have a look at that. Just kind of shows, right, how the subnet mask is changing, and yeah, how the number of networks and how the number of hosts also changes. Right, so suppose we have these two, subnet mask and IP address. Right, okay, let's say we have this, alright, and this one is a bit more complex because it's not like a nice 255. So here basically what we want to do, well, we just want to kind of add up the binary values, and if we do that, then I guess what we actually get, well, this is then going to be the network, right, and well, the device ID, yeah, if we add up, I guess, yeah, all of these, well, yeah, the device ID is right then going to be that. Yeah, alright, so I guess it's saying, well, for humans, things can get a bit, you know, complex if the sort of subnet mask doesn't split on an 8-bit boundary. Although the thing to note, well, for computers, of course, yeah, that doesn't really matter. And that's the thing, right, with subnetting, well, since we can split anywhere, well, then it's going to be much more flexible in that we can only assign a network that's going to give us, you know, kind of enough devices that we need. So if we want 1,000 devices, well, then we can use, let's say, 22 bits for the network ID, right, and 10 bits for the, device ID or host ID. And the reason for that is, well, 2 to the power of 10, right, that's, well, Kibbe, right, so 1024. And of course, well, 1024, okay, so 1024 greater than or equal to 1,000. Alright, so I guess, yeah, just a sort of overview of subnetting. Right, it's going to allow a greater utilization of the IP space, right, basically, well, less wasted IP addresses. Right, it's also going to make the network easier to organize and maintain for large networks, though it does require the initial expertise to set up. Yeah, probably subnet masks, I mean, they're not that easy to set up. Yeah, when you want to think, like, if you've got sort of multiple networks, right, you want to sort of, you know, split them up. Right, however, it is going to improve security because you can have, well, let's say, different firewall rules, right, different levels of security, right, different, let's say, permissions, right, different access roles, right, based on the subnet. So again, let's say, right, the finance department shouldn't have access to, let's say, the research department. Yeah, of course, well, vice versa. Right, well, network separation again. So I guess, what if one part, okay. So let's say if one subnet gets hacked, well, hopefully the hacker wouldn't be able to, you know, spread right to the sort of other subnet. And I guess, yeah, also malware, right? So malware can hopefully be contained, right, just on that one subnet. Right, it's also going to improve efficiency by bringing down, well, big, busy networks, obviously lots of devices connected. into lots of smaller networks. However, this does make it slightly more expensive. Although if you think again, the price of routers, I mean, routers are pretty cheap. So for, let's say, like a large company, I mean, the cost of routers is basically insignificant. In comparison to with like wages and obviously various other equipment they have to buy. Then let's look at network address translation, or NAT. So rather than each device having a globally unique public IP address, then instead, we can simply give the router a globally unique public IP, and then all of the end devices, right, the end devices will therefore only have a private IP. And that private IP is going to be unique for that particular LAN, right, for that particular sort of private network. However, it's not going to be globally unique. That's why you can have multiple people on different networks, okay, but they have the same private IP. So, for example, let's say, okay. So for me, now if I run ipconfig/all, then I think this is probably going to be the IP that I'm going to get, right? The private IP that I'm going to get. Now, likely, if you also run this, say in your house, you're also probably going to get the same IP. Maybe device 1, maybe device 2, right? Maybe device 3, but someone in your house is probably going to have device 1. Okay, so if we look at the private address ranges then. So I guess here we can actually see, okay, so let's try and guess what the subnet mask is going to be for each of these. So if we look at the first one, here we see that the 10 is constant in both of them, right, whereas the next 24 bits, so the 3 zeros, right, 3 255s, right, that's changing. Therefore, the first 8 bits are going to be the host ID, okay, sorry. So the first 8 bits are going to be the network ID, right, and then the last 24, those last 24 bits, they're going to be the host ID. Right, so in this case then what that means, the subnet mask is going to be 255 and then 000. If we look at the next one now, this is a bit harder since it's not kind of an 8-bit split. But if we look at this, here this is the same. So of course, this is going to be 255. Then I think if we look at this, basically you just have to write out the binary of this. And if you write out the binary, then I think what you'll realize is that the first 4 bits of this are the same, right? And then okay, so the first 4 bits are the same, right? And then the last 4 bits are going to be different, right? Compared with the 16 and 31. So because of that, what that means is then we're going to have 4 ones, because 4 ones is going to be for the okay, so 4 ones is going to be for the network ID. Then obviously 4 zeros here, right? That's going to be for the host ID. So if we get that, that's going to be 255.240.0.0, because if we think 4 ones here in the subnet mask, right, that's going to be 240. Right, then if we look at the final one, so I think here just the zeros and the 255s, right, that's changing. Therefore 16 bits for the okay, so 16 bits for the network ID, right, and 16 bits for the host ID. Right, so then if we look at NAT, now NAT is going to translate from private to public, right, also from public to private, so both ways. And if we look at the router here, so the router, okay, so as we mentioned, the router, this has a public IP address, whereas if we look at these, since this is 10, then remember 10, with this particular subnet mask, this means it's going to be a private IP. And of course, if you note, even though they're sort of starting the same, this is obviously device ID 1, obviously device ID 2, device ID 3. Alright, so again, router has public globally unique address, right, device have the private address is unique only for that network. Right, so actually, when we're talking about NAT, NAT is going to make use of ports. So let's just recap what that is. Let's say, right, when a device receives data, then do you think it would be able to tell what process or what application that data is for? So let's say you have a server in particular. Now, maybe on the server you have different protocols that are running, or different protocols that are being listened for. So let's say if you're running a web server, then you're listening for HTTPS traffic. Now, usually HTTPS, that's going to run on port 443. So what you would actually do, let's say you're sending to, I don't know, like 200, let's say 210, right, .220, right, .230. The problem is you can't just send to that IP address, because that particular device is actually going to have very many different processes that are listening for data. Maybe, for example, okay. So as we mentioned, maybe they have a web server, right? Maybe they also have an email server. Maybe they have a database server, FTP, SSH, right, etc. Likewise, even for users, let's say if you've got a browser, each tab is going to have a different port number. So that means that when the data is received, or okay, so when the packets are received, well, those packets can then be routed right to the correct tab, right, based on the port number. So the ports, well, they're going to specify the process that the packets are for. So I guess an analogy, well, if you're sending a letter, then the IP address is effectively the building, while the port number, well, that's sort of, the room number or the person's name, right? So just, more specific. And I guess really there's two, there's hardware ports, well, that's used for input to or output from a device. For example, the Ethernet port, as you can see at the top, and well, software ports again specifies the process, right, that the packet should be sent to on a device. Right, then if we just look at some port numbers, actually, I think in the old syllabus this was required. They would sometimes ask you to sort of memorize some of these. Right, the new syllabus, this is not required. Although I guess if anyone's sort of trying to sort of do some of this practically, then I think it often kind of helps to know some of these port numbers, because if you see, for example, something communicating with port 443, well, then you're going to instantly know, right? I mean, that's going to be web traffic, right? So HTTPS. Likewise, if you know, I know, well, sort of 2021, well, that's going to be FTP. And for example, something like port 22. Now, port 22, if you're running an SSH program, then you probably want to sort of lock down port 22 to an extent. Maybe only let it be contacted by certain IP addresses, and sort of block other IP addresses that are not in the whitelist, right, from accessing that port. Alright, so for example, well, when you type example.com, then your browser is actually going to append the port itself. So effectively, the actual request it's sending as well. Okay, there we go. Right, so example.com and then colon, right, 443. Just to specify that port. Right, so let's have a question then. So suppose my private IP is, well, right, 192.168.0.1. If I send a request to a server, then how does it know where to respond, since this IP is private and not unique? Alright, so this is going to be what our network address translation does. So when packets pass through your router is going to change the source destination, or the source IP address, right, from being your device's private IP to being the router's public IP. So it's just going to swap those IP addresses. Right, then it's going to add a record to its NAT forwarding table, and that record is going to map the private IP port number of our device to the public IP and port number, right, that has been sent out of sort of from the router. So what this means is that when the router then receives the response, well, then basically it can kind of look at this mapping, and it can say, well, if something is obviously come in, let's say, to this port number, well, then it means I need to then send it to obviously, well, this device, this IP, and this port, right, just so it's sending it to the correct device on the network. Alright, so let's see a sort of diagram of how this works. So let's say the user wants to send a request to a web server, and I guess here then, so this is the private IP. Obviously, well, this part here, well, this is the sort of private port. Right, so this is then sending, I guess, well, to right 4030.2010. And if we look at that, well, that's just going to be the web server. So first, then, it's actually going to send these packets, well, to the router, of course, because okay. So if we're starting here, well, first, of course, so they're going to be sent to the router. Now, if we look, well, the router, this has both a private IP, as we can see here, again, 192.168, right, but the router also has a public IP, as we can see here. So what's going to happen is, well, these packets, an entry is going to be made in this NAT forwarding table, and we say, well, on the private side, so this is the device it was coming from, and as we can see, well, that's this device here. Also, I guess, well, this was the port number that the device added. Right, and then if we look at the public side, well, this is going to be the router's IP, and then also, well, just some random port number that we add here. So now, well, these packets will now be sent, obviously, well, sort of over the internet, right, to this server. And again, when the server gets this, well, then it's going to include, right, these details here, this public IP, and also this port number. Right, okay, so then I guess when the server is actually sending the response, so here the server, well, here it's going to respond to the router, as we can see here. And if we look at this, well, port 80, now port 80 is just HTTP, right, so unencrypted. I guess probably this video that I took this screenshot from is, probably quite old. Realistically, again, these days, well, it's going to be 443, right, 443, because we're HTTPS. Alright, so if we see the response, well, here then we're saying, this server is then, well, responding to the router. And again, note that we're also including this port number here. All right, and then since the router has now got this, well, now the router can obviously look at this port number here. So it sees, well, if the incoming packets have are sort of intended for this port number, well, then I need to send it to this IP address, right? This sort of private device, on the LAN, and obviously, this is going to be the port number. Now, actually, for the actual okay. So I guess the router doesn't really have to think about this, to be honest. All the router needs to think about is, this private IP. However, when this device receives it, that's okay. So that's going to be the device that actually needs to take into account this port number, because again, that's how it knows which kind of process to send it to, or which process to forward these packets onto. Alright, so hopefully that makes sense. Right, then if we just talk about two different types of IP address, static and dynamic. So, right, this is the final method to solve the shortage of IP version 4 addresses. Right, that's going to be implementing dynamic IP addresses. And I guess just by the word static and dynamic, well, hopefully we can guess what that means. Right, static IP addresses, fixed, they don't change. Right, dynamic, in contrast, they're assigned by the ISP or router. And there's actually going to be two types. So, let's say your device on the LAN, that's going to get a dynamic IP from the router, and this will also be a private IP. Right, however, your router is going to ask for a dynamic IP from the ISP, and since it's the router, and since the router has to communicate globally with other devices, then that dynamic IP is going to be public. So this is the thing, right? Okay. So a dynamic IP, that can be either public or private. And actually, the way this is assigned was going to be using the DHCP, right, the Dynamic Host Configuration Protocol. And then because it's dynamic, right, therefore a device's IP can change. And probably we'll see that in a minute. All right, so I think this we mentioned. So again, your router is going to get a public dynamic IP from your ISP's DHCP server when it's turned on. Right, individual devices will also ask for a private dynamic IP from your router. And actually your router, that's also going to have its own DHCP server built in. Okay, alright, so if we look at DHCP, so again, a home router is going to include this functionality. Right, this is responsible for assigning a unique IP address to devices that request one, if available. Right, so it does this by storing the valid IP range and the list of currently used IPs. Okay. So I guess if we just want to expand that, so then you can say, then it's going to assign kind of an unused one from that range, which is kind of what this point 1 is saying. But let's say, for example, if we have the range, I don't know, okay. So let's say we have the host IDs, right, 0, 2, 25, let's say 255. Now, if we know that maybe host ID 1 is used, right, host ID 2 is used, host ID 3 is used, and let's say, to be honest, let's say 0 and 255 are also, sort of maybe not available. Since they're also used for other purposes. And actually, let's also say maybe 5 is used. Well, then hopefully you can realize that if a new device is turned on, right? Okay. So if a new device tries to connect to the network, then of course the router's DHCP server. Then okay. So then of course it can just assign that device, the host ID 4. Alright, so how this works, I guess, okay, so since it's dynamic, it's not going to keep this forever. Therefore, the DHCP server will grant them a dynamic IP, right, just for a period of time. And usually this will be between 1 hour to 1 week. And in this example, let's assume 8 hours, just to make the maths easier. So when half the lease time has passed, then if the device is still online, it's going to ask the DHCP server if it can extend the lease, or just, kind of, keep using that IP address. Right, if the DHCP server is unavailable, then the requesting device will wait half the time and try again. So, e.g., if the initial lease time is 8 hours, then the device will wait for 4 hours. Okay, it's going to try, obviously try and ask if it can continue using the IP. If the DHCP server is unavailable, then it's going to wait another 2 hours, right? Try again. Obviously, if right, okay, so if it's unavailable again, then it's going to wait another 1 hour. Obviously, then 30 minutes, 15 minutes. So, for anyone that does physics, I guess it's kind of like radiation, right? The sort of half-life of elements. It's just going to keep halving. Alright, so if it's not renewed in time, then the IP is going to become available for another device. So let's say if we just go back here, now let's say, for example, I don't know, someone turns off device 2, and if, let's say, that lease is going to expire in 1 hour, Now, because they've turned off the device, well, obviously then they're not going to, so because they've turned off the device, well, therefore they're not going to renew that lease, right? Then what that means is, well, this host ID 2, this is going to become available. So then if someone else tries to, well, turn on their device, connect to the network, right, then of course they're going to be able to then take this, host ID 2. Alright, so just to recap about static IPs, so they're going to be reliable, also, sort of relatively easy to access, and I guess that's because they don't change. So if you're trying to communicate with a device, it's kind of easier to communicate with it, if its IP doesn't change. Now, if its IP changes, well, then either you're going to have to update your software to, sort of use this new IP address. Although if you're talking about, for example, DNS, which we'll look at in a minute, now if you're typing in, let's say, a website name or domain name, then even if the IP address changes, well, since hopefully the DNS record will be, so since hopefully the DNS record will have been updated, well, then it's going to use the new IP address automatically. Although even with that, there is kind of like a, kind of like an overlapping time where maybe you, so there could be a situation where, let's say, you try to request the new IP address, via the DNS record, but I guess maybe it's not been updated yet on that particular DNS server, or that DNS record has not been propagated to that DNS server. Anyway, static IP, well, that's suited for servers because, again, a server, generally, we don't want the IP address to change. We want it to be, well, fixed or easy to access. However, disadvantages, well, there's a limited number of IP version 4 static addresses. Therefore, of course, well, if everyone takes them, there's, well, not enough, I think, what, about 4.3 billion. Because of this limited number, well, they're therefore going to be expensive. Just supply of demand, right? If you have, let's say 8 billion people, obviously, well, probably, hundreds of, let's say 8 billion people, probably hundreds of billions of different devices. Therefore, if they're all kind of trying to get those, well, 4 billion static IPs, right, well, therefore it's going to be expensive, just supply and demand. But also less private, because if you're talking about a user, well, let's say if you have the same IP address today as you had, 1 year ago, then potentially if someone can get access to your IP, they would potentially be able to, track you across the internet. They'd be able to, I guess, determine, what sites you were visiting, maybe, I don't know, like what comments you were making, various things like that. And I guess, well, this is related to sort of less privacy. It's also easier to geolocate, because if your IP is, well, unchanging, then, I guess it's easier to detect their location. Right, then if we look at dynamic IPs, well, one is going to be cheaper because I guess, So one reason is that actually, if you have a static IP, then let's say you're using just, a laptop. Now, you're not going to keep your laptop on 24 hours a day. Let's imagine you only have it on, I don't know, 1 or 2 hours a day. Now, that means the other, 22, 23 hours, right, you've turned off the computer, but you're still keeping that static IP address. And for those 22 hours, well, no one can actually use that IP address. Whereas if we think dynamic, well, when you turn off the device, right, once the lease expires, then I guess that IP is going to become available. Therefore, I guess you can say it's kind of like a greater sharing of IP addresses. It's going to be more private again because if your IP is changing, right, it's harder for people to track you over a long period of time. Also manual configuration not required because, well, DHCP is used, and this is mainly for a network administrator. Now, let's say you have, some office building with like thousands of different devices. Now, if you had to manually give all of them a static IP, that's going to take quite a long time. Right. Also, if you get a new device, of course, you have to set it up, right? You have to give it a new static IP address. In contrast, if you think DCHCP, well, in this case, the router is just handling all of that for you. You don't have the network administrator having to manually assign and kind of revoke IP addresses. However, disadvantage, well, they're not suited for servers. The DNS records will be constantly changing, right? Users maybe couldn't access websites, if the DNS record has, not been updated in time. I guess because of this, well, less reliable because, well, again, the IP is changing. And I guess there's also the possibility that no IP is available. So this is kind of the good thing, I guess, with, well, static IP. So even though there's a limited number, right, if you happen to have one, if you've happened to pay for a IP version 4 address, well, basically, that's kind of yours permanently. Whereas the problem is, let's say with dynamic IP, well, maybe you know, turn off your device, and then next time you turn on, well, maybe there's, you know, no dynamic IPs available. Yeah, if you have like too many devices on the network, for example. Alright, so then if we talk about IP version 6, and again, that's also going to be another way we can alleviate the IP version 4 shortage. Basically, just to create a new IP protocol, yeah, IP version 6, and that's going to have, well, vastly more addresses. Alright, and I guess, yeah, we talked about these other methods as well, right? Subnetting private IPs, dynamic IPs, and finally IP version 6, right? All methods to alleviate the IP version 4 shortage. Right, so if we look at the format, right, it's going to use 128 bits, so 2 to the power of 128, right, different IP addresses. I think that's, yeah, I can't remember the number, I think it's like under zillion, maybe 10 to the power of 38, right, yeah, just a huge number. Right, it's written as, well, 8 groups of 4 hex digits, right, separated by a colon. Yeah, so for example, like that. Right, the leading zeros and also one group of all zeros can be omitted. Right, e.g. here, so if we look at the first one, so here we see, well, this is a leading zero, right, a 0 at the start. I guess actually, yeah, so this, yeah, okay, so here, there's also three leading zeros. And here, if we see consecutive groups of all zeros, well, then we can basically kind of eliminate the biggest group of consecutive all zeros. And if we see that, well, the way we eliminate that, just by, as we can see here, so we just got the colon, and then basically, yeah, right, yeah, okay, so all of that inside those colons has just been eliminated. Because if we look, well, here we've got the colon from this one, obviously, yeah, yeah, okay, so the colon before here, and yeah, that's going to be these 2 colons here. Right, okay, so yeah, so there's also, well, a dual format. And the reason for that, well, actually, the transition to IP version 6 has been slow. I think maybe this started sort of 15, right, yeah, maybe even more years ago. However, most people are still using IP version 4. So to allow, well, interoperability, or I guess, well, compatibility, then dual IP version 6 and IP4 addresses can be used. Right, hence, if a receiving device supports IP version 6, right, then it can use the IP version 6 address. While, let's say if it's some old hardware, right, maybe it's some old router. Now, if that only supports IP version 4, well, then it can use that. So let's look at how this works, right? In this dual format, well, 6 groups, and if we think, since this is, well, the IP version 6 part, right, each group is therefore going to have 16 bits. So, well, 6 times 16, right, that's 96 bits are allocated for IP version 6, while 32 bits are IP version 4. And again, that's going to create 128 bits in total. And if we see, well, that's the size of an IP version 6 address. So yeah, the dual format is still going to be the same size. Because if we think, well, 96 bits for the IP version 6 part, yeah, 32 for the IP version 4. And if we look, well, we see here we're going to have the colon. But then if we look at the IP version 4 part, well, then we're just using the dot. And of course, for IP version 4, what again, there's going to be 4 groups. Yeah, well, 4 groups of denary numbers from 0 to 255. Alright, and I guess another example, so here we're just in what the middle group, okay, there we go, yeah, the, well, middle 2 groups of IP version 6 are all zeros, I mean, as we can, well, see that. Alright, so let's think then, so why can we only have 1 group of all zeros? So let's assume we have this IP address. Now here, what, this is going to be zeros, this is going to be zeros. But the problem with this, well, how do we know if what, okay, so how do we know if there's sort of 1 group of all zeros here and, you know, 3 group of all zeros here, right? Or there could be, well, 3 groups of zeros here, right? 1 group of zeros there, you know, or there could be 2 and 2. So if we have multiple groups of all zeros, well, then we don't know how many zeros in the first group, how many zeros in, you know, well, the sort of next groups. Yeah, so I guess that's really what that's saying. So probably what we can do is, let's say, for example, we have, I don't know, maybe 1 group of 0 then, or 3 groups of zeros. We can probably keep the sort of smaller one, and then I guess the bigger one, or yeah, the one with, well, more zeros, I guess that one we can kind of eliminate, right, just to save more space. Alright, so I guess similar to an IP version 4, well, IP version 6 is also going to have a network ID, and that's the first 3 hex group, or the first 48 bits of the address. Right, then there's also a subnet mask. So whereas IP version 4, well, we're going to have the IP address, right, then the subnet mask, and they're going to be 2 separate things. And if we think IP version 4, well, the, okay, so the IP version 4 address is going to use 32 bits. Okay, the subnet mask also uses 32 bits. Whereas in IP version 6, well, here the subnet mask is actually built into the IP address. Right, and actually that's only going to be 1 group, so I guess what's 16 bits. Right, then the device ID, that's the last 4 groups of hex digits, or yeah, well, yeah, hex characters. right, the last 64 bits in the address. So if you think that's going to give you, well, just massive number of devices, right, 2 to the power of 64, yeah, which is, yeah, okay. So that one I can't remember. I think it's like 18, yeah, something. Yeah, I mean, obviously, well, like, yeah, quadrillions or, yeah, something like that. Alright, so there I guess we can just see, right, the different groups. Okay, right, then if we look at DNS, and I think this is the last thing. So if you think, well, what is a domain name? Or hopefully people know that's going to be a website address, you know, baidu.com, right, youtube.com, yeah, abc, right, .xyz. So when you communicate with a server, the computer or network doesn't actually use the domain name, right? Instead, well, hopefully people know what it uses. Okay. So instead, it's just going to use the IP address, right? Hence, there needs to be a way to convert from a domain name, which is easy for humans to remember, to the IP address, which is actually, you know, what's used for, well, the routing process. Right, so this is what, well, DNS, or the domain name system, does. I'm just converting from the domain name to the IP address. Or I guess, like, maybe not necessarily converting, I mean kind of storing a record, yeah, between the domain name and IP, and then just sort of, well, returning the, yeah, sort of corresponding value. So let's say here then, well, this is, I guess, the client, right, just our computer, and let's say here we're trying to find the IP address of, well, mail.google.com, right, yeah, this subdomain. Right, so that's going to go to the DNS server, and if we think, well, the DNS server, this is also going to be in the router as well. But yeah, this can also be, well, the ISP's DNS server, right, the sort of global DNS server. Yeah, okay. So when I say global, well, that's the authoritative name server, and I think we'll look at that in a minute. So I guess for a successful DNS response, well, here then it's just going to respond, right, with the IP address, for this particular subdomain. So then when it's responded with this IP address, well then, okay. So then this is where, well, the client, or I guess the web browser in this case, can of course, well, just send a request, right, to this web server. Well, let's say, 1.2.3.4. So this is, well, let's say, mail.google.com server. Right, this can then, I don't know, sort of get their emails okay. So this can, let's say, I guess kind of get their emails from the database or whatever it's going to do. Right, then of course it can then just send that back to the client. So that's the thing, right, there's going to be a two-step process. Well, first we have to send a request, right, to actually get the IP address, via a, DNS request. Right, then once we've got the IP address, well, then we can actually send, well, in this case it's going to be the HTTPS request. Then if we look at the DNS process, so DNS hierarchical, a DNS record we look for in these places, and I guess if it's not found in the current layer, well, then it's going to be looked for in the next layer. So first we're going to look in the browser and operating system, and I think we'll see that if we just visit a website, then the web browser will store that IP address, or that DNS record. I think it's not very long, okay, I think only about a minute. Now the operating system, this is also going to have some DNS records. Some of these we can also add like a custom DNS record, for example, by editing the host file. So we can add, well, a custom, domain name IP address. Right, okay, then the router. So the router is also going to store DNS records. So let's say if we just visited a website like 5 minutes ago, well, if it's okay. So if it's not in our browser, well, then hopefully our router is still going to store that IP address. Right, if the router doesn't know, well, then it's going to go to the ISP, the internet service provider, right, their DNS server. Right, and if the ISP doesn't know, well, then it's going to go to the root server, right, the root server is then going to go to the top level domain server. Right, this top level domain server, well, this is going to go to the authoritative name server. And this final one, okay, this is actually going to know the IP address, and this is then going to return the IP address. So let's see how this works. So I guess here we're just, okay. So here we're sending a DNS request for yahoo.com. Right, so again, well, first we're going to check, well, okay, so first we're going to check in the browser, right, then the operating system. If they don't know it, well, then we're going to go to the router. And I think here they haven't actually drawn on the router. So let's just draw that. Right, if the router doesn't know, well, then it's going to go to the ISP's resolver. And when it says ISP's resolver, well, the ISP's, right, DNS server, the DNS resolver. Right, so if that doesn't know it, well, then it's going to go to the root server. So this is the top, or the root of the DNS hierarchy, as 13 of these are placed strategically around the world. I mean, the reason there's 13, well, basically a backup, right? If what, okay. So if we only have, one kind of worldwide DNS server, well, one, there's actually going to be, just massive amounts of traffic going to that, right? So it's going to get quite slow. Also, if okay. So if, let's say, some of that data is corrupted for some reason, either like physical damage, hacking, well, then of course all of those DNS records are going to be lost. Right, that's why we have 13, right, just as backup. Also are strategically placed around the world, so kind of placed close to users, basically in so basically placed in the different continents, right? Therefore it's going to be faster, or kind of lower latency, for the user to make these DNS requests. Right, and I guess each root server is going to have its own unique IP address. Right, okay, so then the root server, now the thing is the root server is actually not going to know the IP address of the website. However, the root server will know the IP address of the top level domain server. So in this case, well, since we're going to a .com domain, well, then it's basically going to go to the IP address, for the .com kind of domains. Now, if we're using, say, like a .net, well, then that's going to go to a different top level domain server. Likewise, if we're using .org, right, well, then again, that's going to go to a different top level domain server. Right, okay, so the TLD top level domain server, okay, doesn't actually know all the .com IPs. Again, it simply knows which server to ask. Right, so if we look at this, well, then the top level domain server, well, then it's going to send a request to the authoritative name server. Right, that's responsible for knowing everything about the domain, right, including the IP address. So this authoritative name server, well, this will actually know the IP address of yahoo.com. Right, then that's going to send it back, well, to the, okay. So it's going to send it back to the resolver, or in effect, well, the ISP's DNS server. And the thing is, these records are then going to get cached, right? They're going to get temporarily saved. So this will then store, well, let's just say, let's say like yahoo.com, and let's say, I don't know, maybe 2, right, .3, .4, .5. So this is going to temporarily store that IP address, or that DNS record. Likewise, of course, so this is also going to get sent back to the router. Again, the router is also going to temporarily store that. Again, well, so likewise the browser, right, that's going to temporarily store it as well. Now, the reason it's going to do that, basically, because, well, if we then go to yahoo.com, let's say, I don't know, like a minute later, maybe there's another page on the same website that we click on. Well, then, rather than having to do, of course, this whole process again, well, instead, so instead, well, we just have to check the browser, or if the browser doesn't know, well, then, of course, just, go to the router, for example. If that doesn't know, well, go to the ISP. Alright, so again, well, just a 4-step process, but hopefully people know that. Right, and I think that's what we said. So basically, it's just going to cache it, right? It's going to store the IP address at each stage. Right, so I think the benefits of caching is going to increase speed, also reduce load on the DNS servers. Caching occurs at all stages, browser OS, right, router, ISP, and authoritative name server. Right, okay, so I think the final thing, this is so this is kind of the problem. Now, sometimes we actually do want to add these custom domain records, or custom DNS records. But let's say if you have malware, well, maybe the malware can actually go into the host file. And to be honest, maybe we have, no, okay. Alright, okay. So I think in the other PPT, right, I actually showed it. If you actually want to try this yourself, well, you can just type in host file. So type in, host file, Windows, or host file Mac. You can find the location of this. Right, then, for example, if you try to actually add these custom DNS records, well, potentially then you can actually redirect traffic. So in this case, what we're saying, well, this 58250, now this is actually the IP address of, well, this, right, qq.com. So what this is actually going to do is, well, in theory, okay, when they go to baidu.com, right, it's actually instead going to use the IP address of qq.com. So effectively, it's going to load the wrong website. Now, as mentioned here, or maybe as mentioned in the, okay, so as mentioned here, now I think about 10 years ago, 15 years ago, about 10 years ago, you could definitely do this. Now, when I tried this a couple of years ago, it seems browsers have actually kind of, removed this capability for security reasons. Because otherwise, if you think, well, then you'd have malware that can, maliciously change the IP addresses. And rather than directing you to, let's say, the real google.com, well, they can direct you to, the fake google.com, their own, their own version. Then they can, of course, steal your password, right, when you try to log in. So that's going to be called, DNS hijacking, and it's going to be, a type of farming. All right, and I guess, here's just an example. So even though actually for non-local IP addresses, browsers restrict it, however, for local IP addresses, so effectively anything starting with 127, well, then this will actually work. So here, when I try to go to baidu.com, I guess as you can see here, Well, instead, right, yeah, so rather than loading the real website, well, then of course we just loaded this fake site. And again, this is DNS hijacking. And obviously for a hacker, well, the advantage for a hacker, well, then they can, let's say, have like a fake login form, right? Yeah, steal the person's username, steal their password. Yeah, and of course we'll use that for whatever purpose they want. Alright, so yeah guys, I think that's everything now. I think here I won't go over this again. I would say, well, just pause the video. Yeah, you can have a read of this. Just use it as a checklist. Alright, make sure you understand everything. As always, like, if there's anything you don't understand, well, ask in the comments. I guess you could also go back and watch, some of the more detailed, yeah, individual videos. Yeah, rather than just, yes, well, shorter, but still long kind of revision video. Alright, anyway guys, as always then, hopefully that video was useful and hope to see you in the next one.